Good morning or good afternoon or one of those things. All right. Back for day 2. We're going to absorb yesterday's 4-hour marathon of generative edge AI information. So that's good. We've got Hajar Musanif back here.
Yeah, good morning, Pete. Good morning, everyone, and welcome to day 2 of the GenAI Forum.
Fantastic. And then we have Mike Stauffer, who's a part of the working group, also working on behalf of the foundation based in California. So welcome, Mike.
Yeah, thanks, Pete. Hajar, good to see you today. Welcome, everyone. Looking forward to another good day here.
Yeah, it'll be good. It'll be good. Yeah, we got a packed agenda. We're going to call some audibles as we go, but which is fine. But it's going to be packed full of stuff. Why don't we bring up the slides here, and maybe we can maybe Mike, you can sort of get us through.
Sure.
Remind folks who weren't here yesterday kind of what the deal is here and what we're going to learn.
Yeah. So for those who weren't here yesterday, today's a repeat, different speakers, but it'll be about 4 hours of hopefully very interesting content for you. So I'd like to just first call out our sponsors. Next slide, Razine. You go to our sponsors, Razine. There we go. So I'd like to just thank our sponsors out there. These folks have supported us for all their time, and we're always looking for new ones if you're interested to get involved. But we appreciate the support of all our sponsors.
Awesome.
And if you go to the next slide. So the objectives of today and yesterday were to really understand the current state of the art in generative and agentic AI and edge platforms. We've expanded from the TinyML Foundation to broaden out our focus on all of edge AI applications, including GenAI. I'd like to witness the transformative impacts of the foundation models that make at the edge, discuss the outlook on resource-constrained, energy-efficient GenAI capable embedded devices and their role also on premise, and inspire the community further by creating a unique workspace to move forward on GenAI at the edge through collaborative work. So I think we have a pretty interesting set of presentations today. If we can go to that.
Sure. Well, let's see. This was yesterday.
So yeah.
By the way, we are going to chop these up and put them on YouTube at some point. So actually, if you go to our YouTube channel, which is Edge AI Foundation, youtube.com/@EdgeAI Foundation, we'll put that in the chat. You can see yesterday's live stream in its entirety, but we will chop these up too into more digestible bites.
Right.
But that was yesterday.
Yeah. So today we have a bunch of good prezos. We may reorder these as needed, but our first one is going to be from Evgeny Gusev from Qualcomm, and then Danilo Powell from ST. Let me get my Aruna Kalaru from Dell, Predimam Nachari from MIT, talking about the Nanda effort, Yuri Krustalovic from Liquid AI, Roberto Morabito from Eurocom, and Andrea Basso from MITO. So I'll turn it over to Hajar, and we'll kick this off, and she'll start introducing our speakers.
Let me do a quick PSA before Hajar gets into it. So a couple of things. Public service announcement for those that don't know what PSA is. PSA. So first PSA is this is great. We love being online in our little squares. But if you want to meet these folks in person, AI folks like Hajar and other folks, we're going to have a big event in Milan, Italy, July 2nd through the 4th. We had one in Austin, Texas at the end of February, 3 days, which was awesome. We're going to do it again, European style, July 2nd through 4th at Milan. So you go to Milan 2025, edgeaifoundation.org. Go to our website. You can register. We have discounts for academia. But it's really a great place to meet people, see these types of discussions. About, I think, 45 sessions, 8 workshops, several panels, business roundtables, good coffee, good wine. So come to Milan to meet us outside these little squares. That'd be fun. The other one is, and I'll just show this because we have it, but we have a scholarship fund that provides support for academic programs. We just had one that we underwrote in Malawi, in East Africa. We're having another one in Colombia. These teach educators about TinyML and Edge AI and how to kind of empower their communities. We also provide fellowships and travel grants through the scholarship fund. The easiest way to support the scholarship fund as an individual, first of all, it's all supported by our partners that Mike mentioned. But the easiest way is to go buy some gear at this URL. You can see I'm wearing my t-shirt today. It's nice and warm here in Bellevue, Washington. So yeah, if you want to support the scholarship fund and get some cool gear, then go to that URL and buy some stuff. We've got hoodies and t-shirts, and I think we've got a tank top now. But anyway, so those are my PSAs for today. And then let me turn it back over to Hajar for more this real deal here. What's the real deal?
Thank you, Pete. Thanks, Mike. It's a real pleasure to be with you again after an amazing first day where we explored shifting center of gravity in AI from cloud to edge. And today we continue that momentum with another incredible lineup of speakers from cutting-edge hardware to scalable edge deployments. I invite you all to stay curious, ask your questions in the chat, and engage with the speakers. So let's jump in. Our first speaker is someone very special, not just to this forum, but to me personally. Danilo Pau from ST Microelectronic is co-chairing this working group and forum alongside with me. And I've had the real pleasure of working closely, very closely with him over the past months. His insights and dedications, his spirit, his energy have been absolutely instrumental in shaping this event, this exact forum. And today he'll be talking or introducing papers from a survey. It's a kind of survey of Edge GenAI research, trends, devices, and techniques. And Danilo, the stage is yours.
Thank you so much, dear Hajar. It's really very nice the way you introduced me, and yeah, I feel at home when I'm with all of you and all the time in the working group. So let me share my screen and the presentation. Okay, and then the presentation. During the presentation, I cannot see the dashboard, so hopefully if I do anything wrong, please let me know. Okay, so I assume the slides are visible, and my contribution for today is about different perspective related to generative AI, and I will talk also a little bit about agentic AI from a practical example point of view, and then there is a couple of words that really touch me, and these are the digital divide. And so let me go through all of that. So why spend some of your precious time in hearing myself? Number one, because generative AI deployed at the gap is the biggest source of the digital gap. And I will talk a little bit about it. And second, I will touch the state of art about GenAI at the edge, and trying to prove that this is already a reality in the sense that there are lots of contributions already in place. And I would like to show also some personal contributions about bringing GenAI at the edge using a couple of processors, the STM32MP2 and the STM32N6, which are initial demonstration on our capability to go in this direction. And then this is something I really love because, but why to use GenAI at the edge? I mean, we spent a lot of years on bringing conventional AI and in products since 2018, even before, and now there is this new wave, and that's clearly create difficulties to everyone. So, but let's go first of all in saying that from my personal point of view, that's my opinion. GenAI is the source of digital divide, in the sense that digital divide in 2000 was dividing the humankind in people that got access to the PC from people that didn't have this opportunity. Well, generative AI is order of magnitude greater in terms of impact about the digital divide. Few companies around the world, I would say 5, can master it, have assets, technical assets, technological assets, financial assets, had the operation in place to handle it. Everyone else is out of it. And why? Because that's before the corner year was 2019. On 2019, the memory opportunity, it means the gap between the memory assets of the GPUs and the model parameters of the fixed function AI, was an opportunity because people could devise workloads complex, being comforted by the deployability on GPU. There was enough memory, there was enough computational power. But then from 2019, this trend created the memory wall. And the memory wall is order of magnitude gap between hyperparameterized models, trillions of weights, even more, and not speaking for the data, compared to the capability of the GPU. You may know that the latest from NVIDIA is Grace Hopper. It's a very brilliant type of technology, but you need thousands, I would say millions of that to build up your computing center in order to manage these and these type of workloads, and that's why only few company can manage them and can afford it. But everybody else no. And this happened just in 13 years. And the transition started in 2019, and the consequences are that GenAI is drives the cloud. What does it mean? You need hundreds of trillions of tokens to build up a data set and train such workloads, which means that you need the few one that can master it, need gigawatts, nuclear reactors to power the compute centers. And there is a clear sign that the majors are investing hundreds of billions of dollars to bring up even closed nuclear plants like 3 Mile Island to generate enough energy. The amount of money to train these workloads are hundreds of millions of dollars. Who can afford them? Who can afford this cost? And by using nuclear reactor, the impact on the natural resources is huge, just 2.5 liters per kilowatt per hour, just to manage the uranium all the way the process to use and to feed the nuclear reactors. And the GenAI will generate, millions of tons of electronic waste from now in the next 5 years. CO2 will be increased. Unfortunately, sustainability means that. It's ironic, but double-digit increase of CO2. And how to think that services, GenAI services for the masses, can scale to everyone. We have, last year we had 5.16 billion users between Android and iOS. How can these people can get access simultaneously to any service that fit their needs? So clearly, yes, maybe it's possible, but at the cost of several tens of thousands of compute servers. And therefore, that's really, it's like to say bye-bye to research in the university. it's a farewell of the deployment and the accessibility from small, medium enterprises, the one that are enjoying today the fixed function AI, the conventional AI. And there is a huge bottleneck in accessibility of this technology for all of them. And after all, it's like what happened on 2017, where fixed function AI was on the cloud. Everybody was speaking about smart sensors that essentially were streaming data to the cloud, where unlimited assets were available. And this trend didn't last that much because, fortunately, this community was built on 2018. And in few years, I would say 5 years, but also at the beginning, products were available. Maybe standard microcontroller at the beginning, and now with hardware acceleration, with neural processing unit in single chip, and clearly in the next year, there will be a huge proliferation of fixed function AI. But fortunately, to cope with the cloud gap due to generative AI, TinyML Foundation evolved in what is today Edge AI Foundation, and this created a new hope for everybody of us. So, but let me elaborate a little bit. I mean, is that something new, or in the last few years, there were brilliant examples? Obviously, yes. And in fact, me and Gloria, a student of mine, did a review of the state of the art about GenAI at the edge in the last 3 years, 2022 till 2024, about people who designed and published GenAI model on edge devices. Not saying that this is a possibility, but this has been achieved in the sense that these people not only claimed, but proven that their model were deployable on edge devices. So it was possible to analyze the performances. Essentially, we reviewed 135 selected papers, and only 66 were in the scope, in the sense that were fulfilling the requirement to prove that GenAI workloads were deployable on embedded devices. So little bit of statistics: 20% were a journal paper, 63% were conference paper, and 17 preprint. 48% from IEEE, 17% from Arxiv, 20% from Springer, Elsevier 3%, other 5%, ACM 3%, and AAA 3%. So you see that these are people that put their face in written in scientific papers that have been mostly peer-reviewed, I would say the majority. And so this is a serious stuff. And what emerged is that optimization techniques have been used to reduce the cost. For example, quantization. I mean, there is people that achieved 1 bit LLM. Knowledge distillation, that's the proof that the foundational model are very useful to derive hypoparameterized model for GenAI at the edge with pruning techniques. So optimization are already there, are known, are in many tools already available that are used to design neural network. So optimization techniques are mature and everybody can use them to start from foundational model to achieve what? To achieve different type of use cases. So the task from this survey were essentially more than 45% about visual processing, 5 to 10% about image generation, short language model, text-to-speech, style transfer, and visual question and answering, and the remaining 5%, file swapping, speech enhancement, captioning, translation, and so on. So visual processing task, super resolution, this paper were about super resolution, image enhancement, signal processing, denoising, restoration, in painting, and broadhead rendering. And inference time from few milliseconds to a couple of seconds, all but 3 models were deployed on a smartphone. So smartphone emerged as fundamental assets. Image generation, processor A17, 18, 16, 15, Exynos and Snapdragon. These are the few processors that allowed people to experiment image generation. And models were ranging from 400 millions to 1 million of parameter. Short language model, once again, on smartphones, utilized transformer architectures between 125 million to less than 4 billion parameters. Quantization were massively using. And then visual question and answer, and these I quite like very much. And I would like to mention especially TinyVQA. And TinyVQA from many authors, especially Tinosh, I know very well, Professor Mohsen, and their team achieved on GAPE 8. GAPE 8 is a very low power processor. So that's really with knowledge distillation and integer 8 quantization, that's proven that VQA can be achieved on low power processors. And then text-to-speech. Text-to-speech, a fundamental metrics is a real-time factor, the ratio between processing time and audio length. And we had end-to-end approach like NIX TTS and two-stage approaches, and ranging, and RTF was ranging between 1/100 and close to 2. And also people designed vocoders and implemented on Raspberry Pi and also on microcontrollers. So there were other approaches which mostly were deployed on Jetson, on smartphones, on Raspberry Pi, on some also on microcontrollers, which is good. So bit of statistics about deployable, the device, the end device, the edge devices. Less than 10% of microcontroller. This suggests that microcontroller will have perhaps a marginal role in the GenAI at the edge area. So let's face it. And me personally, I tried with some colleagues to deploy some GenAI task on the STM32 and 6, which embody also an integrated neural processing 3 teraops per watt, style transfers, and the other on the STM32 MP2, achieving some functional implementation about image generation, SLM, TTS, and the like. 10% on Jetson. Jetson, let's remind that this is 15 to 50 watts off the shelf, obviously, and the majority, more than 70%, on application processor mastered by Qualcomm, MediaTek, Apple, Samsung, iSilicon, and Google. So let me go a little bit more on what we did on our processors. In partnership with Fondazione Bruno Kessler, I had the privilege to cooperate with Alberto Ancilotto and Elisabetta Farella. They developed style transfer. Essentially, do you want your face to be painted as a masterpiece? Then we would like to achieve anonymization and personalization and content adaptation. And then a colleague of mine implemented on the STM32 and 6, leveraging the neural processing unit, 10 frames per second. And that's a real-time process. We imported also this demo at the Embedded World this year. So I don't know who was there, but it was possible to see. The another project that I started to compile on ARM 835, 1.5 gigahertz. Our product is called STM32MP2. So that's one. This is the one. And support Open Linux. So I compiled Moonshine, so the Pitwarden useful sensor, amazing speech-to-text model, which is much better than Whisper, but I compiled also Whisper for some comparisons. And then all the C++ project, Llama 2, Llama CPP, Mamba, Lava, and Olama. Olama, I quite recommend Olama because it's easy to manage and give you access to many foundational models, DeepSeek, Gemma, Mistral, Granite, and so on. And also I had some experience on Stable Diffusion. By the way, don't use Stable Diffusion 1.5. There is a brilliant article published by IEEE, which strongly suggests, because the material that have been used by Stable Diffusion 1.5, it's a bit controversial. So I compile as they are, few demonstrations. So this is Olama with the QN 0.5 billions, and I'm just discussing with this Alibaba model and this 2.4 tokens per second. Not that much, but is an initial step. The second is 1-bit LLM, BitNet from Microsoft. That's a brilliant project. Also, this I achieved on MP2 with some initial performances. By the way, if there is ARM people here, please consider to accelerate 1-bit operations in your instruction set, because we are using ARM 835. We need 1-bit instruction acceleration. I mean, this gives enormous acceleration, 32 times, and 1-bit multiplying the accumulate is so cheap in hardware, just an XOR and the bit count that everybody can implement. So please do that. And then I moved on reasoning, and I tried Olama DeepSeek 1.5 billions, and against logical reasoning question with answer from freshers. And actually, it proven to be accurate. And I posted also on LinkedIn some demonstrations. But all of that for what? Why are we so passionate about generative AI? So that's my answer. Because we need it for natural user-machine interface. GenAI is not for another detector. Is not another classifier. People will not understand that because they already invested so much time that cannot go back. So we need to offer a new added value. So how to substantiate that? With the student, we prototypized an interesting thermostat, a consumer thermostat. And as natural interaction, the way to do it was to speak with it, let it reason depending on the query, and let the thermostat speak back to you. So it was implemented on Raspberry. And why on Raspberry? Off the shelf, brilliant Linux system, and a lot of project available, and offer nice performances, but not that nice as real-time would require. So please, Rosina, if you could kindly share the demo, or the video demo.
Can you warm a bit the room?
Also.
I feel cold in the house. Can you warm a bit the room?
Your room will start to feel warmer as I slowly increase the temperature by 2 degrees. I aim to reach a comfortable reference temperature based on today's forecast, ensuring we don't overheat. Would you like to provide any additional preferences, or should I proceed with these settings?
I'm out in a couple hours and I'll be back tomorrow morning. I want the home to be warm when I'm back, but I don't need to heat the house when I'm away.
Okay. Okay, maybe Rosina, can I take once again the control and go back to my presentation?
Yeah, you can move. Those are your slides, Daniel. So you should.
Thank you so much, Rosina. Very kind. So let me explain what's going on. First of all, we were speaking to the mic. The Raspberry was running Moonshine from Useful Sensor out of the box for transcription, and then Granite 3.3. Why Granite 3.3 through Olama? Because it has interesting reasoning capability, which means that after the translation happened, Granite decided to launch a query on the web to understand the temperature outside my room so that it could understand, it could measure the in-room temperature, know the outside temperature, and decide the gradients to warm the room. And then report that to me and let me continue the discussion. So for speech, text-to-speech, we use Piper, which is also a quite tiny model, just a few millions of parameters, and that's the pipeline. So Moonshine, Granite 3.3, and then Piper. So this comes with the complexity. Profiling, it requires Granite 6 gig of memory, 2.36 throughput in token per second, and it was exactly the majority of the complexity was there. Yeah, Moonshine, real-time factor out of the box without optimization, 0.2, execution time 0.5%, 65 megabytes of RAM. Clearly, Granite dominates. And then Piper. Piper execution time, RTF, sorry, 0.13, just 1% of the overall profiling, and 185 megabytes of RAM. So clearly, these use cases require lots of RAM, and this is due to the Granite, but this is Granite with reasoning capability. So clearly, there is a need for energy efficient hardware acceleration. I think it's out of any discussion. So let me conclude and apologize if I took too much time. So generative AI implementation are clearly appearing on edge devices since last 3 years, 2022 and 2024, even before the foundation decided to address with our working group GenAI. So this is established, let me say. And some use cases, even if the minority were meant for microcontroller, are still possible on off-the-shelf microcontroller, like the STM32N6 and MP2. There are, fortunately, the community made available lots of foundational models, and these are brilliant because to derive the students, we need teachers, and with optimized techniques which are well established, including hyperparameter optimizations, then we can derive such models. And then it's clear that generative AI, LLM is just a step. Really, the milestone is LLM with reasoning capability, more complexity, more memory, clearly, but this enables through human-machine interaction at an unprecedented interactivity level. And in my opinion, HMI has a new opportunity, which is to take advantage of the Agentic AI wave, and we need to push forward accelerators with unprecedented energy efficiency. And when I say unprecedented energy efficiency, I would say 100 of teraops per watt, at least. So thank you so much for your attention, and any question, don't hesitate even to ask or just to write to me. Thank you.
Thank you. Thank you so much, Danilo, for the thoughtful and data-driven overview, and also for the demos. I love them. It's very courageous of you to show them, like, especially there is this remark 2 to 3 tokens per second, which I'm going to come up to later. But it's clear that the field of Gen AI is maturing quickly, right, Danilo? And of course, this survey helps many of us map where we've been and where the opportunities lie. So I have 2 questions from the audience. The first question is by Weng, F. Weng. What are the development environments you would recommend for deployment of the models on microcontrollers?
Okay, well, depend on which kind of models. If we are for me, the models can be divided into fixed function AI and Gen Agentic AI. So in the second case, in my, I would say, initial experiment, the capability to use a strong and stable embedded Linux is fundamental. We do deliver OpenST Linux, but also on Raspberry Pi was fundamental because For example, let's take Moonshine. You need UV, and then it was brilliantly engineering Moonshine. Then you need some library to be installed, and therefore the support of Linux and the other Python library is fundamental. So Python abstraction, Linux, Open Linux, I think is fundamental. For fixed function AI, actually, the solutions like our one, which are based on the ST Edge AI core technology, do not need an RTOS. So we just need a strong IDE with capability to compile C code, with strong API, few API to allow application integration. And I mean, ST makes available not only the ST Edge AI core technology, but also another kind of tool depending on the product. So just quickly saying CubeMX for the STM32 microcontroller, Stellar Studio for the automotive microcontroller, MEM Studio for the sensors, and the developer cloud, just to have a try.
Thank you, Danilo. Another question from a LinkedIn user: where do you see a bottleneck to break through? Do you think it will come from community model software improvement first, or from STM architecture improvement, or from ARM NPU capabilities, or all of the three?
I am for open innovation. So I need an innovation, and the innovation I would really love to see are processors that are trying to set the Machiavelli goal, reach the energy efficiency of the human brain. So from wherever it comes, even in a small lab, I don't know where in the planet, I think this is what we need. We are today at hundreds of terawatt per watt, but that's with in-memory computing. That's published on, you see on ISSCC, our papers there. We need more. That's an initial start. And through open innovation, I cannot imagine another way to progress than this.
Yeah, thanks, Danilo. Maybe one last question from me. Given the explosion of interest in Edge Gen AI, what key areas of research or experimentation would you encourage, for example, young researchers to focus on next? Because I see many young researchers there. So what do you recommend?
Well, I was inspired, about generative AI. About generative AI, definitely, I was touched by the paper from Tinosh, the visual question and answering, and also, and I think I shared the demo from what yesterday Pete Warden said, focalize on audio. I think audio maybe is a low-hanging fruit for generative AI, and for VQA, obviously, complexity is higher. So these are the two things, but absolutely with reasoning capability. I think it will be more complex, but we need, I think we are just at the beginning of LLM with reasoning capability. And what I saw is really intriguing, is complex. It's not linear in terms of reason. So there is plenty of progress. In terms of a fixed function AI, I'm still in love with on-device learning.
Thank you so much, Danilo, for that rich and thoughtful overview. And of course, it's always a pleasure to hear your perspective.
Thank you so much.
Now let's move forward with our next speaker. And he's someone who's very, very, very special to me personally. I can even say that I admire him a lot. Dear friend, dear brother, and the one who first introduced me to the world of tiny machine learning. So I owe him a lot. I'm thrilled to have Evgeny Guzev, Senior Director at Qualcomm and Chairman of the Edge AI Foundation, who will be talking about operationalizing GenAI at the edge, from sensor nodes to near-edge infrastructure. Evgeny, the stage is yours. You're on mute. Evgeny, we can't hear you. Evgeny, I can't hear you. Rosina, do you confirm that we can't hear him?
Yeah, we can't hear you. It seems like your mic is turned on, but we can't hear you, Evgeny. So I don't know if you have the permission set up for StreamYard that also audio works.
How about now? Is it better?
Yeah, now
Yeah.
we can hear you. Yes.
Yeah.
That's perfect,
Okay.
Evgeny. And
Yes.
then when you are on your screen,
Yeah.
just don't forget, go full screen and everything, okay? I'll go back.
Yes.
So.
Okay, let me do it again. Share screen. And I go to window and I go to this guy. Okay, and I go to full screen. Okay, so are we all good now? Can you see the screen?
Yeah, but you would have to go in slideshow. It's not full screen. We see your slides next to your first slide.
Oh, wow, I'm actually in full screen. Something is not right there. Let me do it again. So we do full screen. So how about now? Now?
It's not full screen.
It shows full screen on my screen. Okay. Duplicate. Still not full screen?
No.
No.
Okay, let me do a different way then. Let me share the window so that maybe a better way to do it. So that does prove that we have a live stream here, right?
Yeah, that's true.
Do it again. So I do present, I do screen, I do show screen.
Go first full screen on your side and then share.
And I do the entire screen share. Interesting. For some reason, it doesn't want to
Yeah, if you share your full screen, because sometimes if you just share a window, I have seen also yesterday that there are issues, but if you go and share your entire screen, that should work.
Yeah, that's what I'm doing. So I'm going to entire screen and I do share. Let me do it. It doesn't allow me to do the full screen share for whatever. Oh, okay. Now I should be able to do it. How about now? Can you see it now?
Yeah, there you have to switch, Evgeny. Yeah, and then we should be full screen.
Yes.
Now we are
Okay.
perfect. Yes.
And changing pages.
Ready to go.
Okay.
Yeah, you are ready to go then, Evgeny. Yeah.
Yeah, the only problem now is for some reason I cannot change pages.
Oh, you can move. Okay.
I do page down, page up, and it doesn't. Oh, okay, now it's moving.
Yeah.
It's just slow. Okay. Okay. No, I think now we should be good. Good morning, everyone. Can we start?
Yes, you can start, Evgeny. Go ahead.
Okay. Well, again, sorry for this technical thing. Good morning. It's really great pleasure to be here, and especially after the amazing presentation that Danila gave and summarizing why we should be doing Gen AI at the edge and the variety of models that people are developing for the edge. And I appreciate also Hajar, your introduction, and also Danila and you doing this workshop with the team. Really excited to be here, and actually really exciting time to be in the edge space, edge AI space, as we see more and more Gen AI applications coming to the edge. And that's basically what I'm going to be talking today. So I will be covering how we can expand Gen AI horizon with Qualcomm a new Dragonwing platform. So for your information, if you have not noticed this, Qualcomm is known for Snapdragon platform, which is a consumer device, and Dragonwing platform is targeted mostly industrial applications and enterprises, which is different from consumer. It's a new brand that was launched in February, and that's what we're going to be talking today, specifically how we bring Gen AI to the edge using AI on-prem appliance solution. Before this, let me just remind you the edge AI definitions. I think this one I borrow from the ABI research they did with us in 2021, like almost 4 years ago already. And it shows the edge AI extending from tiny ML, which we know and love very well, in the ultra power devices and sensors, as was discussed yesterday, and then going to the intelligent devices like smartphones, and had several presentations yesterday, including one from Qualcomm on intelligent devices, then gateways, and then going all to the on-prem. And today we'll cover this blue dot, the on-prem service. Why on-prem? I think Danilo summarized it really well, that cloud AI, cloud Gen AI is good, it's cool, but it has some issues like privacy, energy, and in general scalability. It gives a very quick way for people to try things and deploy things, but in terms of energy consumption, in terms of privacy and cost, that brings quite a bit of challenges and issues. So that's why we believe that doing AI at the edge is the ultimate way to do it. Again, yesterday we discussed how we can deploy AI at many different edge devices like XR devices and laptops and phones and so on. So that's where Qualcomm plays. And now we're extending these capabilities to the on-prem. So it's more compute capabilities, but it allows to run a lot of Gen AI models, pretty much all the things that can be done on the cloud at the edge. And that's what we believe is the best of both worlds. How do you bring Gen AI, that what people use on the cloud, and bring it to the edge and deploy it at a big scale? This can be used for many different verticals. So I think you can think about like the world around us, like in the retail space, for example. It can be used to help people like digital assistants, kiosks, point of sale devices, video analytics, in the manufacturing, like energy and oil and gas. It can be used to improve productivity, safety, predictive maintenance for the equipment, SOPs, and so on. Like in the life around us, like in restaurants, hotels, and other places, you can think about devices helping to order things, to get some information, to use for promotion, analytics, and definitely big area in the manufacturing, in the robotics, in the warehouses, logistics, in worker assistance, worker safety. So it's basically it's everywhere, it's around, and it's driven by two things: availability of energy efficient hardware, and also models are becoming more sophisticated, models are becoming smaller. I think SLM was introduced last year specifically to reflect that LLMs can be done in a small sizes, like few billion parameters. So that creates this massive momentum to apply this hardware and tools and models pretty much everywhere around, and that's going to be massive. And one area where Qualcomm in particular is very strong is in edge devices. So we can connect these edge devices, like again phones, XR devices, laptops, to this on-prem solution, and that offers people TCO cost savings. Again, privacy, security are very big drivers. We talk to many customers in this space, and customers are becoming, and end users are becoming more and more concerned about privacy issues for a reason. So definitely, Edge AI is a big driver for this, and then also it offers scalability and flexibility there. Just to show one example of this type of deployment, this is a work we did with Aramco, and it's actually going into deployment now. So what you're going to see here, how GenAI on devices. So in this case, we have GenAI running on the phone. It's a computer vision model running on the phone. You can do computer vision, point it to a particular device. It does detection. This is vertical stabilizer or turbine or any other piece of equipment, and then worker can ask like any questions related to the process or maintenance or safety or any other tools. It can be multilingual, as shown here in Arabic. So it basically gives this instantaneous access to company documents and manuals and procedures. Can be also used for safety, like in this case, it is done in combination with drones. And I'll show in a moment like what is under the hood here, how we run this, but this is just to show the use case, how we can use GenAI both at the terminal devices on-prem and have complete solution, GenAI solution running at the edge without using cloud. So this is like you can generate automatic reports and do a lot of interesting things there. And the next one is going to be showing a worker safety. In this case, we are using a combination of, again, computer vision. So you see computer vision here, and also GenAI here using models like Llama type of models with RAG function. You can get a lot of interesting information on what happens in your property, in the plant, compliance, any accidents like here, and it is fully automated. So basically, in this case, it's a great illustration how AI with many different devices can be used to support workers, to improve safety, compliance, and this type of question. Again, a massive opportunity there. And talking about opportunity, it's basically everywhere. So it's in the industrial, in the retail, smart homes, all the fields. I think I am very passionate also about training and education in this space, using GenAI and this type of devices, healthcare, many areas there. So what we do in the on-prem? So the technology itself has two components. It has the hardware and the software component. And the hardware side, we have Qualcomm PCIe cards, and I'll show some details on these cards. They can run really efficient LLM models there, or computer vision models there. And then these cards can be placed in this small box, which we call the appliance. And then it becomes effectively it becomes your cloud, your private cloud, your friend cloud. You can put it in the office, you can put it in a back room, you can put it in a lab, you can put it basically in any place, and you're getting GenAI capabilities at the edge without connectivity to the cloud. So that's quite disruptive. And then on the software side, we offer all the SDKs, platform SDKs, application SDKs, GitHub models, a lot of optimization and so on. And that allows developers and customers and people from the academia and startups to develop their own applications, their own models. Like it can be for code development, it can be for chatbots, for image generation, again, what Daniel mentioned, like stable diffusion type of models, transcription using RAG function, AI agents, and so on. And specifically talking about, again, more use cases and applications there. So this is a platform that can be used for to build applications on top of this. So we have two flavors of this technology. One we call Pro and the other we call Plus or Premium. And depending on the use cases, we can define either we use this or the other one. And again, the use cases are shown there. So it's a lot of use cases, basically covering all possible options that can be done, either connecting it to cameras or connected to terminal devices and doing it in a kiosk type of environment. A lot of interesting applications there. And those some of the things how to deploy this. So you can connect multiple cameras to this edge AI device, or many like industrial handheld devices in the Aramco use case to this appliance, or you can connect laptops or kiosks, and it becomes basically an end-to-end solution for the edge AI without the cloud. So this is just one of the examples. That's what we've been showing recently. You can see this is a very portable device, so like size of a small microwave or small printer. And the cool thing about this from the GenAI perspective, that it is capable of running very large models, like up to 70 or even like 100 billion parameter models. So basically, most of the models that people use on the cloud today, except for maybe like 6 billion parameter models or trillion billion parameter models, are becoming possible to run at the edge. So that's again quite disruptive. There is no more constraints in terms of using models at the edge. And then it can also be done in a hybrid way, so connected to other devices, and it can be done also, as we discussed before, with all the benefits of the edge. So we are basically combining the data center class inference and performance with all the benefits of the edge, like privacy, security, reliability, latency, cost, energy efficiency. So that's again the best of both worlds. Some of those devices are shown here. So working with many companies or OEMs around the world. So as I mentioned earlier, there are several flavors of this. Some of them are good for smaller models, like around 10 billion, some around like 30 billion. And the Premier is for the big models. Depending on this, users can decide what is best for them. It can support multiple users in the industrial environment or smart home environment and other type of applications. One level below, it's all powered by our SoCs, by Qualcomm Silicon. So what we have there, for example, in the standard and Pro cards, there is one SoC, and it can run actually in terms of compute, it's quite a bit of compute there. So one SoC is capable of running up to 400 Int4 or 200 FP16 flops. So that again, it allows really good performance for the LLM and SLM type of models. If we look what we have under the hood there in terms of hardware architecture, so the hardware architecture to be able to support this compute, it's a multi-core architecture. So one SoC, one piece of silicon includes 16 AI cores, and they're done in a parallel way. again, the peak performance for the 16 cores is 400 in 4. It has quite a bit of built-in SRAM memory, so we can do compute on memory without going to the external memory. As you all know, this is very important for GenAI, because most of the energy consumption happens when we move weights and do compute between the memory and compute units. So in this case, we have quite a bit of compute memory on the chip, and then very fast communications there. So this is kind of the architecture of the whole chip. And if you zoom in into the AI core specifically, like one core, it has quite a bit of memory processing with on-chip memory, as I mentioned, and cache there. And the compute itself happens in 2 units. One is the vector unit to be able to process vectors, and the other one is the tensor unit to be able to process metrics. And then there is a tightly coupled memory that supports both of these, also on-chip memory, and there is this scalar processor that operates all of these things. So it's again a very scalable architecture. And by the way, this AI core we use across all Qualcomm products, kind of the basic architecture. So I think what Vinesh showed yesterday, what we have in the Snapdragon, it's kind of similar architecture, similar idea. I think we've been already in the 7th generation of this technology. It's quite mature. So it extends from like augmented reality glasses going all the way to automotive cars. So it's like that's how Qualcomm manages AI cores. So we develop cores and they go to these different architectures. Software is super important, because without software we cannot really run those applications effectively. So we've been investing into the software stack quite a bit. So I think in this case, to be able to run these GenAI models on this device, we support different OS. I think most popular one is Linux, Ubuntu for IoT applications. Then we have a compiler layer. We have layers that allow us to do servings there. And the basic idea here that this type of product, this type of hardware and technology allows us to get models trained on pretty much every popular networks like TensorFlow, PyTorch, or Onyx, and then effectively convert them and run them on our hardware in a very efficient way. And then there is also a layer, what we call Qualcomm AI Inference Suite, that allows developers to design their own applications like chat and AI agents and RAG and code generation and so on. So basically, it's a complete stack that allows very easily to develop applications and use cases there. So the AI Inference Suite specifically is a new feature that we added. It's basically compressed. It's a platform that enables deployment of different models and applications, and it's super easy to use. Like with a simple click, no really big programming experience is needed here, based on OpenAI APIs there. And it's configured for many use cases and supports like thousands of different models, which I'm going to show in a second. And also supports multi-tenancy and scalar and those type of functions, so that it does auto scaling and those things. So it's again a very mature piece of software that allows developers to use this hardware from Qualcomm and develop their own things. And this is just an example of web interface, what this AI Inference Suite looks like. You see some cases like you can generate images, do translate, transcribe, generate code. You can generate chat, do summarization, RAG, and other functions. And these features are model agnostic, so you can use any open source models or most of the open source models, or bring your own model and develop your own application on top of this, and it's based on Kubernetes containers there. It's very flexible. So talking about models, very important topic. Again, Danila gave a nice overview, what is possible, what is happening in this case. So I think we've onboarded like over 1,000 different models there, and they span from computer vision and NLP, what we did like quite a bit in maybe 3, 4, 5 years ago. Now moving more to LLM applications there. We developed a tool called Transformer Library. So this tool allows to pull models from open source, like for example, Hugging Face, and deploy on our hardware pretty much with a single click. So you don't need to go through lines of codes and so on. You just define the directory where you want to get the model from and run this tool, and you get the model deployed. And some of the lists of the models that we support can be found on this GitHub. It's open source. You can go there and find like what models we can run today. Again, all the popular models like Llama models, Mistral models, Quen models, DeepSeek models, all those models can be found there. And I think those are some advanced features we have there. Again, starting from open source foundational models, we have tools that allow to do deployment, monitor tools, do retrieval augmentation for documents. One new feature which we added recently is to be able to do fine-tuning on this piece of hardware. So basically, in this case, we don't need to go to GPUs to do training or retraining or fine-tuning. It can be done on our silicon. So it's not designed for training per se for big models, but it's designed for inference, but it can also be used for fine-tuning. So, and I think the bottom part shows like the RAG pipeline we support. It's a very, very popular feature there. And I think the last and popular question, how can we try it? So I think for developers and for people in academia, we developed these playgrounds. There are several of them deployed around the world, and it's basically a farm of this hardware where people can access this remotely, and it's super easy to go there. You just sign up with your email account. No special paperwork is needed, and that's how people can try this capability. And then on top of this, we have also device management level when companies and people, they can access these devices remotely, then do upgrades over the air, do monitoring, recovery, and so on. That kind of gives a flexibility in terms of deployment. So that's pretty much in a nutshell. Again, to sum up, I think with this new capability, with this new technology, we're really bringing kind of cloud data center quality AI to the edge for the benefits of the edge, like privacy, energy, security, and so on. And it basically unleashes what can be done at the edge with running GenAI models there, and a lot of applications here. Thank you.
And forward-looking presentation. It's exciting to see like this comprehensive approach from far-fetched sensor nodes all the way to near-edge infrastructure brought to life in real-world deployments. And we saw the example of Armadillo, which is really interesting. There are many questions from the audience, but for the sake of time, I'm going to just pick up like two.
Okay.
One from George William. Are there custom tensor units for INT4? He said that he only saw in INT8 and FP16.
Yeah, I think in this generation, we support INT8, FP16, and FP32. I think in the future generations, we do also lower precision units there. But that said, we can support models like, for example, AWQ quantized models, which is we use INT4 for weights and, for example, FP16 for quantization. There are different things we can play with different models here.
Yeah. And the second question, can this card be used in regular x86 PC via PCI Express, or it has to be all Qualcomm platform only?
Yes, in fact, the one I showed, they're Intel-based, so it's 86 platforms with Intel CPUs, and those cards are accelerators, specifically Edge AI accelerator cards, to do it. Like for example, one product that we launched actually last week, that was a Dell. It was a Dell laptop that has Intel CPU processor, and then we have these accelerators inside of the laptop that allows people to run more AI even at the laptop form factor because of the energy efficiency.
And maybe, Evgeny, one last question from me. For developers listening in, what makes the Qualcomm stack developer friendly compared to other Edge AI platforms out there?
We are not comparing more or less. We just want to be developer friendly. So I think in terms of user experience, actually it's a complete stack, as I showed you. And there is all this open source documentation there. So I think the best way is just to give it a try and see it. But it's a complete end-to-end experience there with all the documentation, and it's actually quite advanced from this perspective. And functionality-wise, if you compare to other platforms, it's actually similar functionality there, because obviously, the reason why I ask, I think we want to make sure that yes, software is easy to use and friendly, and it does all the functions that is needed. Yeah.
Thank you, Evgeny, for the brilliant talk, for showing us what it really takes to bring GenAI into real-world edge environments. Now let's keep the momentum going, and our next speaker, that will be, I would say, a deep into the technical heart of Edge AI. And it's my pleasure to introduce Aruna Koluru from Dell Technologies. And her session is entitled Edge Deployed AI Agents, Architecture Optimization and Security. Aruna, the stage is yours.
Thank you so much. The invite, let me share my screen. Can you see my screen? Yeah. Hello, everyone. I'm Aruna Koluru, AI specialist from Dell. It's funny that Evgeny mentioned about the Dell AI laptops. I do work for Dell, and though I don't work in that division, I actually work from the AI specialist division, focusing more on the enterprise deployments. But AI agents has been very popular these days. Let's actually talk a little bit about them. I actually feel we are at a very pivotal moment in the evolution of this AI. For years, AI has lived on the cloud, in the data centers, where powerful models ran behind the scenes. But today, the whole paradigm is shifting. AI is coming closer to where the data is generated on the devices, in our environments, even in disconnected or low connected zones. What we are talking about today is not just AI at the edge, but how these generative AI agents at the edge. That's a very subtle but a very powerful distinction. These agents don't just classify or recognize something. They generate language, summaries, decisions, and even plans of action. The reason they recall from past interactions, they choose tools to accomplish goals, and they do it on device, privately, securely, and often autonomously. This talk, let's actually focus a little bit more beyond the model compression. Let's walk through some of the stack as well as a couple of use cases as well, and why we are here. So Benedict Evans, he's a well-known technology analyst and a thought leader. He spent years analyzing trends in tech, especially around platforms, software, and AI. He's known for his sharp insights and widely followed presentations and newsletters that really explore how technology reshapes industries and societies. His quote actually, I thought like the really captures that fundamental shift on how we interact with AI. Old AI, we called a model to do a task, like asking a calculator for an answer or something like that. With the new AI, you collaborate with an agent, like working with a team member who understands the context, adapts, and helps you reach those goals. It's not just about using AI anymore, it's about working with AI as a partner that can plan, reason, and act alongside you. So let's quickly see what an AI agent is, right? Just a very quick um, introduction. Like AI agent is a system that can perceive its environment, make decisions, and take actions to achieve a specific goal. Um, I know the other considerations are there about the ethical considerations and everything, but this, in essence, that's what an AI agent is. Agentic AI refers to AI systems that exhibit agency, which means that they can autonomously pursue goals, plan, adapt, and make decisions over time, often in complex or dynamic environments. So agents are separate. When we talk about agentic AI, it's about bringing all these AI agents together to work on something autonomously. So we used to think of Edge as a place to run small pre-trained models. These were typically lightweight classifiers or detectors, good for object recognition, sensor filtering, maybe the basic NLP, the outputs for deterministic and narrow, like classify, detect, match. But what's happening now is like this massive leap. We are moving from inference to intelligence at the edge. So mm, in some of the demos, we've actually seen some of the generative AI at the edge. Here, what we are talking about is generative AI agents are a new class of AI systems that don't just answer, they explain, they don't just recognize, they actually generate and adapt. And instead of just inferring, they actually plan. Um, so let me actually talk about an example here, right? Imagine a drone flying over a wildfire zone. It doesn't capture footage. It generates captions about terrain changes, summarizes dangers, and plans the next survey route, all on the device without ever needing the cloud. Or you can now even think about a retail assistant running in store. It watches shelves via vision model, detects what's empty, and generates a personalized promo message for shoppers walking by. All this is happening offline with edge inferencing, retrieval, and speech synthesis. So, how is it different, right? So, this is different because it's actually making those decisions at the edge itself. Now, we've seen like what agents are. I think there are three major enablers for this shift. One is the miniature model, foundation models. We are seeing emergence of high quality models that can be quantized down to run on smaller devices. Models like even Mistral, Phi, Tiny Llama, Gemma 2 billion can be compressed to 4-bit or even like a 3-bit optimized versions. They run comfortably in like 4 to 8 gig of VRAM. This kind of specs you'll find on maybe Jetson Orin, Raspberry Pi with Swap, or like even laptops, right? Evgen mentioned about the Qualcomm and Dell laptops. And the definition of edge is also slightly changing, like, and the capacity at the edge is also changing. And in some of the laptops, the kind of specs we have is quite fascinating. Right now, I have another laptop which actually has like 16 gigs of a GPU in it. And if possible, I'll show a demo, or I'll actually show some of the screenshots I've got from the demo. I'm actually running like multiple of these models simultaneously as AI agents at the edge. And these AI agents actually also push that move towards more domain specific models. When we say domain specific models, we want those models to be um, very small, trained on specific data. So that also drives smaller models to be run on that. And then the second part of it is the agentic frameworks. Having the model is not enough, right? You need to give it a structure. Frameworks like LangGraph lets you define the DAG-based planning flows where the agent makes decisions and passes context from step to step. And then we have AutoGen that allows agents to use tools, memory, and history in conversational loops. And then Crew AI organizes agents into role-based teams like a planner, a verifier, an executor, really enabling that coordinated workflow across different agents. These frameworks are the glue that turns a single model into an intelligent worker, or like a swarm of them working together. And then the last one is the edge native runtimes and tool chains. Deployment is now easier than ever with projects like Olama. It's like a CLI and server interface or a runtime for running quantized LLMs locally with REST endpoints. And we have llama.cpp, like, which is like a optimized C++ runtime with GGUF model support, token streaming, and flash attention. And then you have LM Studio, desktop app to run and chat with the local models, and WebLLM and WebGPU run LLM models right into your browser, even on a phone. These tool chains make it possible to deploy agents on mobile devices, embedded systems, or even into your browser tab completely offline as well. So we have this agents in sync, right? So once we have all these multiple models, the agent communication gets very, very important. And the newest protocols which have been released in the last few months, Model Context Protocol allows for the AI agent to talk to all the environment and the tools around it. For example, if an AI agent, which we are talking about, the planning agent, wants to look at a disaster from a drone, and it want to talk to a weather app to look at what's the weather next, to make the decision of what are the next steps. It could do that, or it has to send this message to so many people. It can actually interact with other tools to do that. MCP allows a standard way of doing that. Before MCP, everything was like everyone had their own way to interact. Most often, a JSON was used as an output and input to other agents. But with this one, like, you have a standard way to interact with things. And then A to A is like an agent to agent protocol from Google, which enables, again, a standard way for agents to talk to each other in a standard way. So, and you might have seen, like, lots of enterprises are actually releasing their MCP support for their tools, so these agents can talk to them. And this is a very, very high level example of how multiple agents are interacting with MCP, the diagram there. And then we have Generative Edge Agent. Now that we have actually spoken a little bit about the shift, what we're talking about here is not about a single model running on the device. A true agent is more like a modular intelligent system capable of perceiving, thinking, remembering, even deciding and acting, all in a constrained environment. Let's break down into the 5 essential traits for an agent, right? Perception. This is where the agent actually connects to the real world. It might be from the microphone, the voice, camera, video, or even a sensor like temperature or GPS. This actually is your maybe like an audio transcription or image analysis, motion detection, etc. That can be done on the device. And this local perception is what makes edge agents situationally aware. And then we have the generation. This is the agent's expensive or the expressive cognitive power. This can generate natural language response. It can generate task summaries, decisions. This is what makes generative and not just reactive. And the third one is the planning agent. This is the intelligent loop. Instead of just operating one output, the agent might need to decide a sequence of actions. Frameworks like LangGraph or Auto this is where reasoning happens, deciding what to do next, not what to say. And then we have the memory. Edge agent isn't very useful if it forgets everything between the sessions. Agents use local vector databases like Face. Face is actually a light version is not available, but if you don't compile a GPU version, it actually is a pretty light to store relevant context. This lets them remember previous user interactions, learn from the usage, and retrieve past data even offline. This memory actually makes them contextually aware and personalized. Um, and then we have the tool use, perhaps the most agent-like behavior. Agents can call APIs, run scripts, query databases, or control hardware, like maybe turning on the lights or activating a drone. This is where frameworks like AutoGen shine, combining generation with tool invocation logic. This makes them actionable, not just smart assistants, but autonomous workers. Together, these five pillars from the complete edge agent architecture, right? They actually make that complete architecture. And so this one is like a few examples. These are not prototypes or far future concepts. These are deployable AI agents running on edge hardware today. Let's explore a couple of these cases. Autonomous factory agents in industrial settings like manufacturing plants. A vision transformer model can detect irregularities like misalignment or broken parts. A local LLM, maybe a Mistral 7B, generates a defect report in natural language. If needed, it triggers a robotic arm or files an alert for inspection. This whole inspection process um, is automated. It used to happen, and this can happen without any calls onto the cloud or to a data center. Agents are embedded in line, continuously learning from failure patterns, stored maybe in light databases like maybe SQLite, or queried by vector databases. And then rural health assistants, imagine like a health worker in a remote village. They speak into a mic. Patient has mild fever and a cough. Last night, gave maybe like 500 milligrams of paracetamol at maybe 10 p.m. or something. The agent uses Whisper for local speech to text. Then quantized models like Phi summarize this into a structured clinical notes. A local vector databases allows the agents to recommend protocols or verify previous symptoms, and the response is read aloud to the clinician using a text to speech fully offline. This setup brings contextual autonomous support to places where there's no connectivity without compromising any privacy as well. And in disaster response drone, in emergency zones, a drone scans a flooded area, feeding images to some of the image or object detection, like maybe YOLO or any object detection tools. And then we can also use a SAM to segment if required. And then that data, or you can also send it to something. What I've done in the demo is used Lava, which is a multimodal model to really identify the scenario itself, not just the objects in the image. This agent generate captions like maybe floodwater has breached and car stranded or something like that. And then it uses a local LLM to plan the path for human responders or other drones. The agent can now log this to local memory, generate like a visual map overlay, or broadcast a summary over maybe LoRa or ultra low bandwidth scenarios. Again, here there's no delay, just actionable intelligence on the device itself. And the last one is the personalized retail advisor. I spoke about this. You can use a camera to track the stock values, like how much stock is there on the shelves. AI agent identifies what's missing and creates real-time offers or restock requests. The system can interact with shoppers using audio. Would you like a discount or organic oats, right? Maybe these agents are powered by local Olama runtime, Imagine encoders, and Whisper-based audio feedback. It's a personalized, private, and adaptive experience powered by Gen AI at the edge. So these examples span different industries, but this share the same principles. I wanted to pick like a completely diverse examples, but the underlying it's the same, right? It's a local inference, contextual generation, it's autonomy and privacy. They'll demonstrate the incredible versatility of Gen AI agents in different areas. And then in agentic AI applications, data traverses through model context protocol. It facilitates structured interaction between a language model and its evolving context, whether it's the memory, tools, or the environment. And then we have the A2A protocol, enables agents to communicate, delegate subtasks, or coordinate workflows. And we have this shared infrastructure, which includes external APIs, tools, vector databases, file systems, or even buses. And then I did not represent here, but I was actually thinking wherever you see those agents, right? Scout agent, planner agent, and the communicator agent, each one should operate within its own isolated security zone, enforcing the principle of least privilege. This segmentation actually ensures that if one agent is compromised, others remain unaffected. Inside each agent, we actually see the model context protocol. This governs how the agent language model interacts with its evolving context, like previous tasks which it has done, or the memory or tools it accessed. Maintaining the confidentiality and integrity of this context is crucial because it often contains sensitive information, for example, customer profiles, intellectual property, or a workflow state. And then we have the A2A protocol. Between agents, we have the agent to agent handoff. This is where agents communicate, delegate tasks, or share partial results. These handoffs must be tightly controlled and auditable to avoid data leaks and privilege escalation. This layer is a potential vulnerability if a summarize agent or like one agent, the scout agent, receives raw undetected data from the researcher agent, it might unintentionally expose sensitive information downstream. And then we have shared infrastructure and the risk surfaces. At the bottom is a shared infrastructure with all that all the agents may access. This includes the shared memory, where all the agents store and retrieve intermediate state or long-term memory, and external APIs like web search, databases, or internal services, and then tools like file processor, translations or calculators, and vector databases or file storages, which hold embedding spaces or contextual data. These components form like a risk surface. Why? Because they often cross trust boundaries. For example, an API might log queries, a tool might behave unexpectedly, or a vector DB might be queried by unauthorized agents. So all these actually provide those barriers. So far, we talked about what agents do and how they are structured. Now, let's talk about how we get these large language models, small and fast enough to run at the edge. So, model optimization has advanced dramatically over the past 18 months. We know about quantization. That's the most impactful trick. It reduces the bit of the model weights. We all spoke about that. I'm not going deeper into that, but tools like GPTQ, AWQ, and XL2 helps you quantize with minimal loss of performance. This reduces memory by 4 to 8 times and improves inference speed significantly, a must for edge device. And distillation, um, quantization compresses, but distillation actually learns. A smaller model is trained to mimic the outputs of a larger model. Phi is a great example of that. It only has 1.3 billion parameters, but punches above its weight because it's distilled from GPT 3.5 like data. This technique helps you retain the knowledge while fitting the edge constraints. And then we have Allora or Qlora, which are like fantastic for making age-friendly fine-tuning practical. Instead of updating all model parameters, you train and store only low-rank weight deltas. These are tiny, usually under 100 MB, and can be merged into a base model at inference time. So yes, you can actually do on-device fine-tuning, which enables personalized or domain-specific agents without retraining them from scratch. And then so there's some runtime tricks, right? Like the final layer of optimization. Use GGUF model format, the standard in Llama .cpp for optimized disk and memory handling, and enable flash attention to speed up the context window operations. Use fused operators and quant-aware token streaming for low latency interaction. With these optimizations, you can actually serve a 4-bit model at 10 plus tokens per second on something like Jetson. So now let's explore one of the most powerful capabilities of the agents, multimodal reasoning and tool using. Um, Multimodal means the agent understands more than the text. It can actually take in images via encoders like SAM or MobileNet or variants, um, and audio using the Whisper CPP or Teams for speech to text. It can also read sensor values. Multimodal inputs make agents aware of the real world, not just what users say, but what's happening visually, physically around them. And then generative output, these agents aren't just interpreting data, they're gathering decisions, right? Creating captions for images, tree fallen on the north road, right? Or summarizing events or commands saying that flood detected in whatever sector, rerouting this particular drone, or responding verbally or visually via text to speech or UI. And they do all this on device And then we have the tool using behavior. This is what separates agents from assistants. Agents don't respond, they act. Once they process the context and reason over it, they can actually call APIs locally or on a LAN, trigger scripts or shell commands, or actually control hardware, like maybe actuate a motor, toggle a sensor, send a LoRa signal. This turns the agent from passive the demo itself. If we have time, let's go there. And now we actually
Aruna, if we can't hear you anymore, I think you have some network issues because you always go like silent and now you were off, but we can't hear you anymore. No, we don't hear anything. So Yeah, sorry everyone. As Evgeny mentioned, it just shows that we are live, and that just happens. So let me know. Okay, I'll do that. I'll bring you on the other. Okay.
Can you hear me now?
Yes, yes, we can. Okay, we'll go with that.
Yeah.
Okay, no problem.
Apologies.
That's okay.
So we've talked about the input perception and output generation and planning. Now we reach a critical capability that makes edge agents truly intelligent over time, and that's memory. When we say memory, we don't just mean saving logs. We are talking about contextual memory that lets agents adapt to previous interactions, personalization that reflects the user, environment, or situation, and retrieval based reasoning that enriches generation using stored knowledge. And let's unpack this, right? Like local vector databases. To store memory, edge agents use vector databases that are on device. Like I said, Face can be a good example. For example, CPU, not a GPU based version. And then, for example, you can say summarize previous visits by patient ID, so and so. The agent queries its face index and returns records, notes, or even like audio snippets. This is how agents build contextual intelligence. And then the retrieval augmented generation, we pair vector memory with a local LLM using RAG, which stands for Retrieval Augmented Generation. Tools like Llama Index and GPT Cache make it possible to pull relevant memory chunks, feed them into a prompt, generate a personalized, up-to-date response. This bridges the gap between static LLM knowledge and the dynamic user-specific context. And then we have the personalization with memory and RAG in place. Agents can remember a username, history, and preferences, maintain tone or style consistency, track repeated questions or issues. This enables use cases like a retail agent that recalls a shopper's previous interests. And some of the light embedding models like MiniLM, E5 Lite, these are small, fast, highly accurate, perfect for edge inference. All of them can run using sentence transformers or even in llama.cpp style environments with slight tuning. In short, this memory layer is what separates a generic chatbot from a true agent. And then we want to really focus on these agents, not just generating, but they need to plan, sequence, and act across multiple stages. So let's explore the 3 agent planning frameworks that are incredibly relevant here. LangGraph, again, it's a DAG-based planning. It lets you build agent flows like graph, where each node represents a step. A memory retrieval planning tool called validation. You define the edges that describe how state flows from one node to the next. You can loop, retry, verify, or even branch based on outcomes. This is ideal for multi-step tasks on agents. An agent might first retrieve prior context from a vector database, then plan a response, then call a tool for the API, then verify the result. Because LangGraph is local executable if its edge workflows perfectly. And similarly, AutoGen, we spoke about AutoGen, and then Crew AI. It actually provides role-based multi-agent teams. Crew AI takes it further by letting you build a team of agents, each with its own specialty. A navigator that plans the sequence, a verifier that checks the constraints, a responder that interacts with the user. This is powerful for multi-agent orchestration on edge. Especially when agents need to handle different modalities or responsibilities. You can use this even on Jetson device by assigning roles to smaller models or tasks. We have seen how powerful and autonomous these edge agents can become, but this autonomy comes with a responsibility, especially when agents are making decisions locally, generating content and interacting with the real world. Now let's talk about the governance, auditing, control for edge deployed agents. Encrypted local stores for all local memory, especially user data or logs, must be stored securely. Use encrypted file systems or abstractions like OpenDAL, Open Data Access Layer. This helps agents store memory, retrieve data, or action logs in a way that will that are actually tamper resistant and private. Edge does not mean insecure. In fact, local encryption is often more trustworthy than sending data on the network. And then tool call whitelisting and scoping, since agents can call tools like scripts, APIs, hardware triggers, we need strict control, define scope for what they are allowed to do, use whitelisting to restrict which tools are callable under which conditions. For example, a nurse assistant can generate reports but not modify medications. You want functional autonomy, not free for all behavior. And then we have the audit log, right? Every agent decision, tool call, and response should be logged, not just for debugging, but for accountability and compliance. These logs should be structured, time-stamped, and stored locally, and optionally, they can be synced to your secure hub. This enables auditability in regulated industries like healthcare, defense, and finance. And then the last one is the hardware-based trust. More edge devices often come with hardware-backed security or hardware-based security. That's the trusted platform module and ARM trust zone or encrypted SD cards or secure boot environments. Use these to verify that the agent runtime hasn't been tampered with, that the models are signed, that memory is not leaked during execution. This is especially important for mission critical or safety sensitive agents. And then the emerging protocols, we spoke about MCP and A2A on a standard way and a secure way to communicate. And there's also Cisco ANP, which is the AI network protocol for secure agent-to-agent communications. And IBM's work on FHE, that fully homomorphic encryption for private model inference, even on edge hardware. These are building the secure fabric needed for decentralized AI systems. And then let's take a step back now and look at the patterns, right? The common blueprints of how edge agents are deployed in the real world. These are repeatable designs that show up. By any means, these are not like comprehensive. These are some of the patterns. On-demand agents, these agents are user-triggered. Think of a retail kiosk or an airport translator or a field assistant, right? They wake up when the user interacts, maybe a button press, voice command, or even a gesture. They load models, respond intelligently, and shut down or idle when not needed. These are energy efficient and suited for public-facing or battery-limited environments. And then we have the event-driven loops. Here, the agent is always listening to a sensor. Maybe it's monitoring temperature. Maybe it's monitoring temperature, motion, or light or audio. When a threshold is crossed, like a spike in the noise or an object detected, the agent is triggered. It then runs a pipeline like analyze, detect, and act. You see this in smart factories, security cameras, environmental sensors, or something like that. And then we have tool-enhanced reasoning. Some edge agents are not just responders, they are planners with capabilities. They use local tools like maybe a calculator, GPS, SQL function, or like a file system or an external hardware. They reason over context and decide when to use a tool, like uploading a report, opening a gate, or sending a local message. This is like true autonomy, where the agent thinks through actions and executes this local resources. And then the swarm coordination. This pattern is emerging. Think of multiple drones, robots, or devices that each run their own local agent. They share sensor data, learn from each other, or coordinate tasks all within themselves. You will see this in agriculture or wildlife monitoring or disaster response or even in military field intelligence, right? Swarm agents act like distributed teams, adapting to conditions, collaborating, and improving what they're doing. These patterns are not just theoretical, they're being deployed right now, and they help us design systems that are resilient to failure, fast to respond, and flexible to deploy anywhere. How are we doing with the time? Like, is there time to switch for a live demo, or should I actually go with the slides showing screenshots of demo?
You actually exceeded the time by 10 minutes. So, yeah.
Okay. I'll quickly, 1 minute, I'll take 1 minute. This is actually 3 different agents trying to take the input. And what these agents are doing, I had like multiple agents here. You can see for the Scout agent, I have a model and a YOLO model. And for the Planner agent, I had a fee, and a communicator agent, I have a Mistral model. And when I actually upload an image, it actually generates a report like this. This is the image I've uploaded, and each agent actually sends the information to the next agent, but you can see it identifies the whole image, what's there. This is the output from the YOLO, and then it identifies the whole scene from the lava, and it actually plans on what has to be done from the output of the Scout agent, and the emoji in the last communicated agent generates a report to publish it to everyone, communicate of what is happening. Sorry, I took no time, but
Thank you, Aruna, for the very informative talk. I mean, it was really interesting, this deep dive into the architecture and optimization of edge deployed AI agents, and also the demos, which are really interesting. For the sake of time, I'm going to pick up again 2 questions from the audience. One question from George Williams: since agents are based on large or small language models, are they also vulnerable to hallucinations? And are there ways to quantify this in agentic deployments? And what are the best practices to reduce hallucinations at the edge, ESP, in resource-constrained hardware?
Yeah. So irrespective of whether it's edge or in the data center, agents are always like domain specific, right? So we are not going on a very broad range of questions when you're asking them. You actually have a set of data which you train them for a very domain specific purpose. For example, when I used just the YOLO model for the demo, it was just giving me a random thing saying that it's a boating experience, right? Even when there's like a disaster. That's the reason I'm actually using that in combination with a lava model, which has the holistic context. So the domain-specific models trained on specific data is the one way to reduce the hallucinations, to give the data which it is responding to. So I assume there'll be less hallucinations by having domain-specific models responding just to those questions.
The last question is by Vikash Kodati. And regarding the vision to action slide, like flood detection and rerouting, are they already being offered as a service from Dell?
It's not a service from Dell. Dell actually offers multiple endpoints, like the edge devices, ruggedized hardware to deploy in the disaster-like situations or anywhere, maybe on a truck or something. We have had many use cases where these things are actually deployed on the truck, right? So if a disaster, for defense, for agriculture, all these were deployed on the truck, like in ruggedized environments. And also the latest version of the laptops have quite a large GPU memory. And all the models I was showing on that demo were running on one laptop. So, and they're not like a very small optimized models. I was running Mistral and YOLO and Lava and Fee, all 4 of them on the same laptop at the same time. So they're quite capable. The models are becoming more powerful and the devices are becoming richer.
Yeah. Thank you so much, Arun, again for the insightful and technically rich presentation. And let's now turn to a different but equally exciting domain, which is decentralized AI ecosystem. And it's my pleasure to introduce our next speaker, Pradyumna Shari, who will be sharing his work on Nanda, an open protocol designed to enable secure, collaborative, and interoperable networks of AI agents. Pradyumna, the floor is yours.
Thank you so much, Hajar. I hope I'm audible. I'm also going to be sharing my screen. And hopefully my screen is visible. Awesome.
Not yet.
Not yet? Okay.
Yes, perfect.
Okay, perfect. My computer has a bad habit of stopping screen sharing in the middle. So if at any point something looks weird, please feel free to poke me so that I can correct it. Thank you so much for having me here and giving me this opportunity to talk to you about something that we find very exciting, given the time that we all live in, given the space of agentic AI and where it stands today. First of all, I'd like to thank the organizers for putting together such a great lineup of speakers, excluding myself, of course. But as someone who's not traditionally within the Edge AI space, I've learned so much from all the presentations that have come before me, and I'm sure the ones that will come after me as well. So today I'm here to talk to you about some of our work at the MIT Media Lab, which we call Nanda, Networked AI Agents in a Decentralized Architecture. There's a lot of fancy words in this acronym, and I hope by the end of this presentation that I'm able to explain to you our goals, aspirations, and what we intend to do with this project Nanda. So a bit of contextualization. Over the past couple of years, we've seen a massive growth in the space of AI, especially with these large language models such as ChatGPT, Claude, Gemini from Google, Grok from XAI, and so many others that have really changed what one can do with machine learning, deep learning, AI models, and just knowledge assistants. These models have global knowledge across domains of expertise and have truly taken the world by storm and have really transcended the boundary between engineers and technologists to becoming learning-based products and tools that are usable and understandable by humanity at large. More recently, and as Aruna was mentioning right before, we are now in the realm of what's called agentic AI or AI agents, which are large language models or models based out of large language models that are not just reasoning capable, but also action capables. In other words, these are large language models that have some kind of agency or the capability to take actions based on their reasoning. This growth or this change that we are or improvement that we are seeing in AI and large language models is actually very analogous to the way sort of mainframes and PCs developed into what we view as the web as it exists today. So AI models from a couple of years ago, like ChatGPT, are analogous to the mainframe PCs that we had in the 70s and 80s, which were individual sources of intelligence, let's call them, but were not able to communicate outside themselves with other intelligent entities to do tasks beyond their own capabilities. From there, the sort of mainframe PC era moved to what we call the intranet, which is computers and PCs that are able to talk to other computers and PCs that they know exist out there. And this is similar to how agentic AI is today. AI models, large language models, and agents are able to talk to other agents that they know that exist already and sort of interact with them within their own ecosystem, talk with them, communicate with them, and do agentic tasks. For example, let's say a cloud provider has 100 agents, each of them capable of doing certain tasks such as scraping the web, researching topics, looking up academic papers, and then these agents can together within this known topology talk to each other and do some complex agentic task. Today, we are at a phase which we call decentralized agentic AI, which means, again, as Aruna was saying, with the advent of all of these amazing tools that enable all of us to deploy AI agents, such as Crew AI or LangChain, that make agent deployment very, very straightforward and a low-code to no-code solution, we're at a stage where almost all of us are capable of deploying our own AI agents, connect them to specialized databases and tools, and build uniquely capable AI agents. Each one of us is able to do this today, and each one of us can do this anywhere in the world. So we exist in a world of decentralized agentic AI, where agents exist in a trustless economy. I don't know all the other agents that exist out there, and that limits my capability to leverage all of this agentic capability that exists out there on the internet of agents. So this is where Nanda comes in. We want to take all of this amazing decentralized agentic capability that exists already and that will exist, especially on the edge, and build protocol and infrastructure layer tools to enable all of these AI agents to discover each other, find each other, talk with each other, and sort of interact with each other to do tasks essentially. So imagine the World Wide Web as it exists today, which are millions, hundreds of millions of web pages and domains that I don't already know exist out there, but I can easily access via their web page names, find web pages, do tasks, and sort of serve the web seamlessly. Now imagine if each of these web pages was agentic, each of these web pages was intelligent, could do agentic tasks, could be autonomous, and could collaborate with other web pages or other agents to do things that are beyond our wildest imagination. This is what we want to envision with Nanda, a networked architecture for AI agents in a decentralized ecosystem. We often like to motivate this with a fun example of a birthday party. So today, when I have to organize a birthday party for someone, for my family member, for my wife, I will have to do 10 different things. I will have to send invites to all of my friends, ask them when are they available, what are their calendars looking like, look at their calendars, figure out what their availability is, then separately reach out to the grocery store, ask my figure out whether grocery store A has all the inventory that I need to host the party, then reach out to a bakery separately and figure out whether bakery A has the cake that I want or if I have to go to bakery B, and all of these multi-dimensional optimization problems. Now imagine if all of these entities had intelligent agents, and I too had an intelligent agent of my own. I could just tell my intelligent agent, organize a birthday party for X, invite all my close friends, and buy all the inventory that I need to host this party correctly. The AI agent would be able to talk to other AI agents of people, of shops, look at other people's calendars via their AI agents, and do all of this optimization on its own. This seems like almost a dystopian reality, almost a far-fetched reality. But this is something that AI agents are actually capable of doing. Of course, this doesn't exist today because there are a lot of very critical problems that we need to solve before this becomes enabled. These include problems like privacy, data markets, verifiability, authentication, how do UI UX development to ensure people can easily interact with such tools, and of course, making onboarding to such an ecosystem easy, democratic, and widespread. This is the goal of Project Nanda, or the Internet of AI Agents, which is how can trillions of AI agents collaborate across organizational silos, communicate seamlessly, navigate autonomously, socialize, learn, earn, transact on our behalf. Nanda comes with a bunch of its own algorithmic, economic, research challenges. These include new discovery mechanisms. How can I discover AI agents that exist out there that I don't know of, that I want to potentially interact with? How do I verify and transact with these AI agents? How do I incentivize the existence of this open web of AI agents? And how do I build what we call knowledge markets or intelligence markets, which is how do I value the intelligence or knowledge that other AI agents are providing as we interact in this web of AI agents? At Nanda, we build off of some very incredible work that people in industry are already doing, and we view this Nanda project as a quilt almost of all of the critical components that we think are necessary to enable this web of AI agents. This includes obviously critical communication protocol aspects, such as Aruna was talking about earlier, protocols such as MCP or Model Context Protocol from Anthropic and A2A or Agent to Agent from Google, but also so many other things that are required to enable this web of AI agents. These include how to ensure trust between unknown AI agents, how to enable safe transactions for agentic AI, how to enable or how to create foundational layer attributes such as protocols for communication, aspects such as registry to enable discoverability and search, and how to enable the building of applications on top of all of these foundation layer aspects that this web of AI agents requires. Uh, as we come from an academic institution, we are also very excited about all the research problems that exist in the space. These include how to build better AI agents, how to ensure that these AI agents are interfacing with data in a private manner, how to ensure verifiability, orchestration, valuation, and user interfacing. As I mentioned already, we are inspired by a lot of exciting work that's already happening in industry in the space of decentralized agentic AI and interfacing AI agents together. These include Model Context Protocol by Anthropic, which is a way to connect tools to AI agents, and A2A by Google, which is a protocol that provides specifications for how agents can talk to each other, how agents can uh, evaluate each other's capabilities, and build teams to perform tasks. All of these exist in the communication layer, and we build on top of these to bring together other critical aspects that are necessary to build this web of agents. These aspects include, of course, how can agents discover each other without actually knowing that they exist, how to enable something like a search for AI agents, which is actually a very, very non-trivial task. Think of Google search that exists on the web, but something that is enabled by hyperlinks and HTML text that exists on web pages. And think of how AI agents are actually very implicitly defined. So there's no hyperlinking between AI agents, there's no text to search against. So how do you build search functionalities for AI agents? But also aspects such as authentication. How do you authenticate AI agents, especially agents that are likely to behave autonomously on their own? And how do you verify or trust them? And finally, trace. How do you instill accountability in autonomous AI agents? How do you pair them with physical world entities to enable sort of accountability, reputation, authentication, all that tasks? At the Media Lab, we've been working on problems along these directions, leading up to where we exist today in the space of AI agents and agentic AI and decentralized agentic AI. So we are very, very excited as we embark on this open source project, which is Nanda, which is a broadly collaborative project. And I'll now talk about some slightly more technical stuff that we are building as part of Nanda to enable this web of AI agents. So the motivation for this and sort of our guiding North Star as we build this web or internet of AI agents, this democratic internet of AI agents that anyone can sign on to, anyone can add their AI agents to, and communicate via, is we sort of take inspiration from how the World Wide Web developed. Also, incidentally, sort of strongly pioneered here at MIT via the W3C consortium and by Tim Berners-Lee, I'm sure we all know. And we sort of take inspiration from how the World Wide Web developed, but also being cognizant of how agents are very, very different from how web pages were. Agents, for example, are dynamic, actively respond and adapt, unlike static web pages. Agents can operate where needed. And this is sort of very relevant to the forum we are at today, which is agents can be at the edge. Agents can be small models deployed on edge devices such as robots, cell phones, household devices, and so many other things that maybe we don't even envision right now. And not just from centralized servers. Agents can have location mobility based on demand, based on operating at the edge, while web pages remain static. Agents are consumer driven, heterogeneous, and involve bidirectional communication, which means as opposed to web pages, which are a very clear client server model, agents are actually a very clear peer-to-peer model. Agent A can reach out to agent B for their services, whereas at a separate time, agent B can reach out to agent A for their services, and it's a very bidirectional and flat hierarchy, essentially. And finally, agents have a clear notion of teaming, where multiple agents can reach out to each other, delegate tasks based on their expertise, and work with each other to complete certain tasks. So, with that being said, I'll now talk to you about one of the critical components that we are building as part of the Nanda architecture, which is this idea of a Nanda registry for agents. So, as I spoke about earlier, agents are likely to be very different from web pages and are likely to have very unique attributes such as dynamism, uh, specific skills and goals and attributes. And we believe that one of the critical components that is necessary to enable key aspects such as verification, authorization, identifiability, and discoverability of agents on an open web of agents is the idea of an agent registry. We view this agent registry as a lean registry of entries, of agentic entries that map agent identifiers to a couple of things that I'll talk about soon, but broadly mapping agent identifiers to agent endpoints and enabling all of these agents to be discoverable on an open web of agents. Here's a simple architecture, very, very simplistic architecture that you can think of when we envision this open web of agents. Think of the registry as an entity that enables identifiability and discoverability of agents at the center. Now, any two or more agents that want to talk to each other and find other agents that perform certain specific tasks can use the registry to find useful agents. For example, Adam agent on the left maybe needs to find a bakery agent in their vicinity, and they can use the registry and all of the attributes that the registry possesses that I'll talk to you about soon to discover the bakery agent and find where the bakery agent is hosted via its endpoint. And then once the registry returns to the Adam agent, the bakery agent, the Adam agent can then, on its own, without the registry in the middle, talk to the bakery agent, do an agent-to-agent communication, and talk via whatever protocol the two agree upon. So we want the Nanda registry to be sort of a universal, democratic avenue for agents, resources, tools of all kinds to be visible and discoverable via the registry. And sort of once we do sort of the initial handshake via the registry, we want the agents to do their own thing. So talk to each other with the protocol that they prefer most, talk to each other in whatever terms, transact with each other in each other's terms, and so on and so forth. Now, the registry is not just for agents, but also for resources, tools, such as calendar resources, analytics tools, inventory tools, so on and so forth, that can be teamed together to build very, very powerful interactive agentic applications on top of this open web of agents. So as we try to build this registry, we again take inspiration from the current web architecture, which includes critical aspects such as domain names, metadata databases such as Whois databases, addressing schemes such as IP addressing schemes, and certification such as certifying authorities that enable verifiability in today's HTTPS-based web architecture. And we see whether this can be applied to the agentic web. And we hit certain roadblocks because of fundamental differences between the traditional webs and the agentic web. As I talked about earlier, the traditional web is reactive, whereas the agentic web is proactive. The traditional web includes manual navigation of web pages, whereas the agentic web is likely to involve intelligent AI agents which navigate on it on their own, and several other distinctions that make a traditional web-based system difficult to directly translate to an agentic-based system. We also take inspiration from how humanity developed from dial-up to broadband. So if you recall, and I barely recall because I remember that this happened maybe 20 years ago, which I barely remember, where initially internet was served via telephone lines. And at some point, we decided that telephone lines are not going to be sufficient, and we need to move to a specific broadband infrastructure. And this was based on some reasoning, but a lot of leap of faith. But this has served us very well because this has enabled some critical aspects, such as it has solved a bunch of known challenges, but has enabled new applications such as video serving, content delivery, and media serving that one would not have envisioned at all when the World Wide Web was developing. So as we move from the web of web pages to the web of agents, we should not constrain ourselves to the traditional web to interface agents, not just because of problems we know right now, but of all the things that agents will be able to do in the future that we just cannot envision as well today as we start. Especially in the context of Edge AI, and given the scale that Edge AI promises with edge devices in the billions potentially, these AI agents are going to likely be in the scale of billions at some point in our near future, and there is a need to think of the infrastructure in that context. Of course, as I mentioned, there are several potential issues with the current web infra, including aspects such as latency, security, traceability, verification, and also scaling challenges, given that the web infra or the AI agents infra is going to scale to many, many agents, piggybacking on the popularity of Edge AI, the Internet of Things, and also aspects such as personal AI agents, where we'll hit several fundamental challenges that traditional web faces, including addressing limitations, certification propagation, metadata requirements, and so on and so forth. With this context, I come back to very briefly talk about what we at Nanda are building, which is a registry for AI agents that is trying to solve some of these issues that we envision will happen as we scale up to dynamic, implicitly defined, large volume, and mobile AI agents. The Nanda registry that we envision is a sort of hierarchical multi-layer registry to enable support for dynamic agents. This includes three layers. The first layer is what we call a lean registry that maps AI agent identifiers to metadata URLs. The second layer is a metadata that is very descriptive and talks about all of fundamental aspects that we think are necessary for AI agents to discover each other, identify each other, and transact with each other. And the third is a dynamic resolution layer, where we rethink what it means to serve AI agents across the world in a distributed fashion, and have them be discoverable and identifiable. First layer is a minimal registry, which contains some very, very simple things, which includes an AI agent identifier, as well as certain links to what we call agent facts, which are metadata attributes that associate to aspects that are necessary to identify AI agents. The key benefits of having such a lean registry that just has a name and a link to some metadata attributes is that the registry does not store direct endpoints or capabilities, and has low churn, high resilience, and reduces the number of read-write cycles on the registry, which is very, very critical to ensure scalability and also ensure all of the metadata attributes that we think are necessary for AI agents to interact with each other. We envision that this registry will be deployed in a hybrid model to make it democratic and deployable across different kinds of agents that exist out there already. So these include agents such as enterprise agents, public agents that are decentralized and low stakes, public agents that are high stakes that require centralized certification, and many other types of agents. So again, within Nanda project and within Nanda registry, we hope to bring all industry, academic stakeholders together and build together a global registry, a global slow source of truth, broadly, that people can build on top of and use to build cool applications, such as search mechanisms, discovery mechanisms, trust mechanisms, reputation mechanisms, and so on and so forth. The second layer is this facts schema, which is a bunch of these metadata aspects that are stored separately and in a decentralized manner at every agent to ensure the agent can declare their uh, existence, their name, their endpoints, their capabilities, and their trust elements, such as third party auditing of agent capabilities, third party auditing of agent sort of skills, and aspects such as dynamic routing, which are very, very critical. Uh, as I mentioned again, this is sort of a visualization of how we view this registry to be, as in a two-hop fashion. The first is a lean registry that points to agent facts. This agent facts points to several critical aspects of the agent, including endpoints, usage formats, certification, capabilities, discovery, and this leads to the actual agent via an endpoint. Again, as I mentioned, we view this registry as a source for initial handshake. And once agents have discovered each other, they do not need to come back to the registry to find each other, and they can do their own peer-to-peer decentralized transaction as long as they satisfy a specific time to live on the registry entry, which is taken from traditional web. The final aspect is this idea of a dynamic routing, where we rethink how agents will be served across the world uh, in uh, in the form of multiple endpoints that will exist for agents. These can be in terms of load balancing, these can be in terms of geo balancing and reducing ping requirements. Also, in terms of certain agentic applications that may be resilient to slow routing times versus fast routing times, and then deciding which versions of agents to serve depending on these aspects. I'm touching upon this in a pretty high level because of limitations on time, but we also have a bunch of papers that we've written on these domains. So I encourage you to check those out, and I'll drop the links at the end of the session as well. In the end, as I conclude this, I want to show you a quick demo of what we've already built on top of the Nanda registry in terms of some applications to show you some of these agentic interactions that can be enabled via the Nanda architecture, via the Nanda registry, across communication protocols that span industry boundaries, basically. So here is what we call Nanda Chat, which is a simple front end that enables AI agents to talk to each other. So first, what you'll see is two people, Adam and Mary, father and daughter, talking to each other via their AI agents. Mary's asking Adam a quick question, which is, "Can I? Where is this? Yeah, can I watch a movie tonight?" And now this message goes via Mary's AI agent and reaches Adam. In this case, this AI agent is tasked with making the message more agreeable to Adam, whatever that means. So it translates Mary's message to Adam, shows it in a certain format, and displays it to Mary. Now, Adam would reply to Mary again through their own AI agent. And Adam tells Mary, no, you can't go to see the movie because you have an exam. And again, Adam's AI agent will take the simple message and retranslate it for Mary, make it more complicated. So this is one type of interaction, agent to agent, that is possible. But there are other types of interactions as well, which is agent to entity. In this case, Adam is trying to talk to a bakery to try to place an order. And this goes to the bakery. On the other end, the bakery is talking to their own personal LLM agent, figuring out what Adam prefers. This LLM agent gives bakery some query, some idea, and then via this context that the bakery gets from their own personal LLM agent, the bakery can talk to Adam via their LLM agent. So the bakery agent also tells the bakery what their inventory is by connecting to other inventory tools using MCP. And now, based on all the context that the bakery has, the bakery will go back to Adam and tell Adam what kind of cake can be supplied to Adam. And this communication is via agent to agent or A to A. So in this very quick demo that was powered by the Nanda registry, you saw that Adam could talk to talk to his daughter via the A2A protocol. Adam could talk to bakery via an A2A protocol. The bakery could talk to its inventory via the MCP protocol. Adam could talk to other stuff like this, all powered by the Nanda registry, and sort of democratic across different communication protocols such as A2A, MCP, also other protocols that exist out there, and all of this stuff. Uh, Today, the Nanda project, and I realize I'm just about out of time, so I'm going to end in a minute. So the Nanda project is an open source project that includes a bunch of academic partners, a bunch of industry partners as well, who work with us in many different ways, including hosting a distributed registry, building services on top of the Nanda registry that add value to the registry, helping us build open source code, and all of this stuff. So with this, I'll end my presentation. Thank you so much for listening, and happy to take questions. If you have any further questions, if you want to join the endeavor, please check out this link. And thank you so much.
Yeah, thank you, Pradyumna, for the great presentation. And the demo is really fascinating. And the vision of like decentralized network of AI agents that are secure, autonomous, and also interoperable is really ambitious. And I really congratulate you for that. There are many questions from the audience, and some people like simulated what you did to Corba, the Common Object Request Broker architecture. And this is a comment by Farhan Malik. Now, Nanda sounds like Corba, web services and other distributed system architecture realized in the age of artificial intelligence. And he was wondering, like, what percentage of internet communication do you think will be agent to agent, say, like in 5 years, for example?
Yeah, this is a great question, actually. So, love the analogy, and I think you're likely to be correct over here. But in terms of the second question, which is what percentage of internet communication is likely to be agent to agent, I think if we look at the velocity that the space has in industry today, so as I told you, all big players are launching their agentic services. Salesforce has something called Agent Force. I know that companies like Dell, Qualcomm, all of whom are on the call today, I know are working on their own agentic pieces. Uh, uh, Companies like Microsoft recently launched something called NL Web. I don't know if you've heard about this, but this is a way to make any web page that exists out there an agentic piece. So any web page that exists out there becomes something that you can talk to via an agent. So looking at the velocity in the space that exists out there, I think a good percentage of web traffic is going to become agentic. I think 5 years is a long time frame. Looking at the speed at which is working, I think we are looking at 1 to 2 years at this stage, and a lot of it is becoming agent. As you rightly pointed out, George, there is a lot of fun stuff about this. This seems so exciting in terms of what it'll enable for the future, but there are a lot of valid concerns in terms of security, privacy, control over our own data, and so on and so forth. And one of the goals that we have within on the project is to do all of this in open source, in open with stakeholders from neutral institutions and industry, so that we don't just build better and better agents, but we build tools to ensure that these agents are behaving in an ethical, trustable, private manner, so that we reap all these benefits, but also ensure that core tenets of privacy are maintained.
That's great. There's another question by Farhan Malik. Does blockchain have a place in a Nanda-based architecture?
Actually, a very strong place, I would say, because if you go back to the sort of quilt diagram that I showed you, there are several components that actually blockchain technology is actually very good at. So I briefly touched upon another registry, and blockchain has several good technological innovations such as decentralized identifiers, public sort of peer-to-peer systems, and trustless verification, which are likely to be very important as agents scale up, especially for edge devices, right? As they come and go and become ephemeral agents, sort of blockchain-based trust mechanisms, where you do decentralized identifier-based verification rather than going back to a centralized verifying authority. These are going to be very, very critical as we scale up to billions of agents. Of course, transactions and stuff like that also. I think blockchain has a big role to play. in this architecture.
One question from my side. I mean, there are those agents that are built with entirely different goals, entirely different models, maybe infrastructure, etc. I mean, how does Nanda approach the interoperability when we have those different agents?
It's a great question, actually. Well, there are two ways to go about it. One would be that the community decides on one protocol. And the second is that we support all protocols that exist out there. So the approach we are taking right now, as you can kind of see from the demo that I showed, as well as we are trying to be supportive of all the protocols that exist out there and try to support as many as they can. But we do think that the industry will coalesce into one protocol moving forward. We just don't want to dictate that for anyone. We want all stakeholders to come together, try it out via something like a Nanda platform that just brings everything together, and then decide what is the unified protocol. But my bet would be that this is going to unify together in the future. And if you actually look at a lot of those protocols, they are actually very, very similar, because in the end, these are all large language models that are talking together in text, right? Now, it's only a function of what JSON dictionary is being passed between one to another. So I do think this is going to condense down into one thing, but we want this to happen democratically. We don't want to be the ones dictating this.
Maybe one last question. Like, for example, if organization who want to get started with Nanda, what are the prerequisites they should prepare for?
Yeah. So please go to the webpage, nanda.mit.edu. We have a bunch of ways in which organizations can interact with us. You can be sort of open source contributors. You can be thought leaders. We also write a lot of academic papers. I think Edge AI is a great space for us to get expertise from all of you guys attending here, because we are not experts in Edge AI. We are more experts in decentralized AI. So that's a great perspective to have. And of course, help in open source, build, deploy services on the platform. So please go to nanda.mit.edu. We have a bunch of resources, and hopefully you reach out to us via that.
Thank you very much, Pradyumna, for this fascinating and forward-looking talk. And with that, I'll hand it over to Mike, who will be moderating our next block of sessions. So, Mike, the stage is yours.
Thank you, Hajar. Well, very interesting set of talks so far. So let's continue now with Yuri Krustalov from Liquid AI. Liquid AI is an interesting new startup, also out of MIT. And Yuri, I'll hand it off to you. I think you may be muted, Yuri.
That's correct. That's absolutely correct. Thank you. In order to be here, let's begin. This would be a small talk about more on-hands experience and what others can learn, what we learned here, and maybe we will share something for the community next. Agenda is pretty simple. We'll speak what is Edge. There are many definitions, and I've heard few of them today, but in reality, Edge is something more and controversial, and you'll see, it's just amazing. Then challenges, how one who builds for the Edge, what would they need to consider? What is this? Resources, approaches. When you look at the guides in the internet, there'll be examples that mostly are incomplete. And it's quite difficult for someone who is new to this to start. We'll touch executors and some simplifications on this. Okay, philosophical thing. What is edge environment? Is when I step out of a home, is it edge or not? We define here at Liquid that anything that has no PyTorch is edge. Because in PyTorch and VLM and all of these facilities and fascinating tools, you have everything for running a model. You don't need anything. So when you have no umbrella ML framework that is available at runtime, you're on the edge. Edge is when there is no CUDA. It's when you need to think how to perform, how to infer this data. When there is no, let's say, de facto defined easy way which works out of the box. I can go outside and I can get into the taxi, and it will be something like CUDA or PyTorch. But if I need to walk, if I need to plan my path, my way, no, this is the edge. There are constraints. So when you're operating on something where it's not infinite, when we look at the modern GPU boxes, a lot of memory, a lot of GPU, a lot of compute resources, you can do many things and you can be inefficient. It's already working. But on the edge, in order to get something barely working, you have to invest a lot. You have to do some work and efforts just in order to run something on a very simple, primitive level often. Also, on the edge, you're restricted. The operational system that you're running is likely some closed source or semi-closed, and you are forced to packaging solution. You need to bring everything from where you compiled it. You have to be tiny. You have to be self-contained. You're limited. And often the edge is not about just endpoint. You're part of some application. So there is someone else who has a business need, who has a particular idea they want to evaluate. They are using this edge deployment as the part of their application. So you're constrained from different sides, and you're offline. You literally cannot utilize other box. Well, obviously, one smaller box can use some bigger box and so on, but there'll be some place where you would say this is the end. You cannot go to the internet. You cannot use anything but this computer, these resources, these GPUs and CPU, everything. And it all leads to the following characteristics of your solution that you'll be working on the edge. It would be very tailored. So you cannot build something that supports all the backends, all different types of inference. You will pick a few, maybe one, likely one, maybe two. It's not designed for fine-tuning training or anything like this right now. I hope it will, but once we are there is no edge in the previous sense. So on the edge, when we are doing the inference only thing, we are decision makers. We are in the final stage. There is nothing then, if our model returns something and it's convincing us, it just says, get it to the user. You have to get it to the user. There is no other way you can work around this. It's very hardware specific. So we will talk about different vendors, providers, and a lot of them are today available in this conference, which is great. And they're all actually quite different. Despite they're trying to achieve and solve this similar problem, the way how their software and hardware works is quite different. So the edge solution always tries to match the particular instruction set, particular memory model, particular I/O capabilities, particular all of these restrictions. ARM is a good example. When you have ARM and you have x86, you have different things. Some operations may work differently. They may be different precisions. They might even have errors, because if you're relying on a third-party library that is built for a particular assembly and it's rarely used assembly, it may contain error. You have to optimize and think about being limited all this time. So, good example, your model is quantized. You just cannot simply afford it as is. Your context window is limited. So if it's a KV cache-based model, transformers, you cannot accept infinite window. You're limited on this. And your OS, will always get you that an amount of cores you can use, amount of memory, background process, all of this, always limited. Also, it's a different mentality of whom you're building this for. You are an entrepreneur in some way, because you have a client and their client have their own client. So you're likely building for an app developer who is serving some end user. and hence you need to be convenient for them so they can use you, and their application quality really depends on your quality of your inference, on your solution. You're the tool. And probably the most interesting aspect at looking at the edge is that you are measuring the model. If your model worked great during the training time, and in the GPUs where you measure against other models on different arenas, and all look great, but after doing this, lowering to a particular backend, quantizing, limiting the context window, it may turn out that the quality of the model is very different. It's not the same. And you cannot claim to someone, our GPU worked great. No, it doesn't matter, because your final deployment is on this device. And if this device doesn't perform well, that's the model. So what is the interface? We're quite in an age of modern internet where everything is internet, distributed systems, networks. But there used to be a concept of complete software where things were not updated at real time. They would be implemented once and living in this state for years. Now, every day you receive a new version of something, and it's very easy to live in a GPU world on a service side, as you can deploy any change anytime, obviously. On the edge is different. You're planning for getting this thing to be untouched, staying for a cycle, 6 months, year. Oh, at least it's not daily. So whatever you plan, you have to think, what is my interface? How I expose whatever my inference engine is. And we know there is a good protocol, OpenAI. A de facto is a protocol everyone uses, the chat completions. The only downside is that it requires the internet, so we need an HTTP. Yeah, you can run it locally, but you then need to expose local host. You can force the client application to use it. Maybe they cannot. Maybe there are constraints on the devices that you cannot open the port. Maybe it's iOS and so on. So you need to think of different type of interfaces. Command line interface, probably the best interface that humanity invented since the beginning, and chat API, chat completion is literally the command line interface continuation here. And you need to think of it. How I can have my tool, my model being interacted where the only thing is bash or something that is limited and acting like bash. Obviously, the C interface. With it, you can try to incorporate your engine whenever you can, anything, because the definition of the operational system is a need of the C compiler. Often, I think it's the reason all this operational system exists. So, if you have the minimal bare bones C interface, now you're deployable almost everywhere. For the benefit of bigger applications, C++ interface. This is more interesting because now you can think how I can get my model available on Swift, Apple, Qt, Windows applications. It's very essential. You don't want your app to be so isolated, your inference so isolated that someone who uses it needs to now pack two different things. You want to be embedded. And GenAI is another example where we have Android application and you want from the Java or Kotlin layer pass your invocation down to the C and then to whatever you implemented. And here is a small diagram that shows you that the main idea I want to hear you take away from this is that inference engine is something that has interface, and there should be more interfaces than you think. And probably the lowest level interface is the C interface. And then everything else is being built on top. And Llama CPP does a good job on this. Now let's look at consumer devices. So it was a fascinating 15 years since the Android and Apple iPhone were released. and they're competing, they're producing something new. And what we have right now is this matrix, a table of a platform, the architecture, flavor, and possible backends or engines that they have for executing some compute-intensive tasks. Let's just pick a few of them. Android. We all know Android as a consumer thing, and ARM8 is probably the most popular architecture and flavor. And there's a great company, Qualcomm, who've been here today. They have the Edge SDK. But also there is an XNN pack framework by Google that allows executing all these ML operators on purely on a CPU. But there are also less known things for Android. Is ARM7 or x86-64 for the simulator. And if you take into account, okay, I want to get my app that I am an end developer creating for my consumers, and I'll be using some ML tool and I would need an inference engine incorporated. And if I build it, now I need to think about 3 flavors. And if I'm using different backends like XNN or Qualcomm, this is multiplied now by 2, so it's 6. You see that complexity evolves immediately, and we just touched Android. If we go further, iOS, Apple, a great company, but also they have quite steep complexity. If you look at the number of flavors they support, so iPhone, they have a simulator. Simulator has 2 flavors. The iOS is single flavor, but Mac and iPad, they share something called Catalyst, so where you can use iOS UI tools for the Mac, and they're built differently, and they are technically different flavors when you compile them. With Apple ecosystem, we get about 7 flavors just to cover all the common platforms they support. But if we, on top of this, incorporate CoreML, which is the framework from Apple for computing-intensive tasks, and XNN pack as an alternative that works on a CPU, now it's 14. And this grows. We have a huge evolution of Windows with recent, again, mentioning Qualcomm Snapdragon, but with AMD as well, the AI chips, that your computer becomes something capable of running this inference locally. And there is a divide, there is a split. So modern Windows computers are more likely to be more performant if they are using Arch64, which is ARM-based. And if you try to compile the same software for Windows, it's already a challenge when you have something that is originally designed for Unix to be precompiled on Windows. Now you have 2 different platforms, and you have Qualcomm, AMD, XNN, and possibly more to follow backends here. Just mention for the sake of existence, Raspberry Pi. It's a great platform because Raspberry Pi 5 can handle about 10 token a second 1 billion model if you compile it correctly using just XNN pack backend. And speaking of regular Linux, well, it's probably the easiest platform to support because it just works out of the box in most cases. But what is this thing in terms of a development? You are a developer. You are reading another how-to or manual on the vendor side, and I would say, you know, our something runs only on this Windows, or on this version of Windows, or only on this particular Linux distribution. And it becomes hard. How you can cross-compile it, how you can cover this table by the software you developed on something just one flavor, how you can make sure that things that you develop locally would be possible to execute on all of them. You need to verify it somehow. But before, let's mention other things that an edge developer, and we're Liquid, we're very concerned of, and we think these things should not be viewed distinctly. They are related and they are the inference. It's just they are not mentioned often, but let's mention here. We know that there is a forward method, but it's not always only the forward method that you need. You need the way how you transform your inputs. So maybe there is embedder that exists that translates your original consumed from the client side input into something your model understands. There is always a tokenizer or a set of tokenizers. It's not common that we probably public narrative says one model, one tokenizer, but not always the case. Sometimes you want to build something more complicated, and there are reasons for this. Multimodality, for example, or switching the models depending on a particular input. And tokenizer may be designed for a particular language that is not popular, for example, English, but you may even want to produce your own language and your own tokenizer. So a good example might be function calling, where you have some functions defined as tokens and their inputs or their arguments also as tokens. So you get into special token metrics and so on. You don't want to limit this. You need to consider it as something that is bound to a model and is distributed next to the model. So meaning that tokenization process and de-tokenization process is part of the inference. And it's not just you taking something from the shelf. Maybe you have to implement your own rules. Maybe you need to have post-processing in order to all of this make sense. Grammar manipulation. So there is a new trend in the AI ML industry where you just say it's not about what is the capital of France, but I want to get a very precise answer. I want to have a JSON where it would be just city and then Paris. I don't want the model to return me back some text which is has some temperature, some randomization in it. Here, grammar things come in place. So now you need to think how I can run my model so that I can take the logits which are produced during the inference loop on a single step and tweak them according to the rule set which is grammar contains. And that literally means you need to hook into the process where the loop happens. Most of the frameworks, they're keeping you distant. They're saying, well, you can do this, but here is a DSL or domain specific language, some way you tell our engine to do this, and our engine does it for you. But it turns out that you can actually look at it more deeply and closer and implement everything in a single subset of a language that would run on all of the platforms. Sampling. Another thing I mentioned, that if you look at the Llama CPP as an example, you'll find there are a few sampling tactics, but not necessarily your solution needs them. Maybe you need something else. Again, from a consumer standpoint, it may be not that obvious, but there are more than just top end. There could be low M and different temperatures and different ways how you want to eliminate particular tokens and so on. You want to multipass maybe. Back to the HTTP interface. So we know that there is an OpenAI thing, but my small inference on my smaller device, maybe I want more than this. Maybe I want gRPC. Maybe I want to have specific authentication. And all of this need to be considered. How to get it, how to incorporate it and make it part of this deliverable file system. Just simply remember in C++, only CPP 17 added the file system. So the common, before this, you had to use boost or some other techniques how you operate with how you deal with the file system in your particular case. Looking further, okay, there is Android, there is iOS, and they handle it very differently. You need to obtain permissions, you need to get things incorporated, handled properly. There might be caches, there might be some other restrictions. Your model, how you distribute it, how you load it, what is the process of obtaining it? Will you have an HTTP connection during the inference? Like Llama CPP offers us, you can say, this is the Hugging Face place, and you can pull it and then invoke it. But what if you don't? What if you need to have it ahead of run, where you store it? Maybe your model is trained on some private data. It was mentioned RAG many times. We know that RAG is a technique where you can inject something that is not meant for someone else's eyes. But sometimes you maybe have a model that is not public in some sense. Its architecture might be public, but its data, it's not. And you want to protect it. You may want to encrypt it. You may want to have some layer of security so not everyone can use it. And usually inference doesn't solve it. But just coming back, how you build a full solution if you have all these pieces in mind and you need to incorporate them all in once. Not even speaking of memory. So the memory, and we all know that if you're running Android, it can decide that if the application is too memory consuming, it could be killed. So you lose efficiency. How you can restore it quickly, how you can eliminate recalculations. We'll speak of this. So compiling all of this together is a challenge. And if anyone tried doing a pull request to Llama CPP would know that a full cycle of executing all the CI would be about 9 hours. And if you try to do this privately, it would cost you about $200 because of the time the GitHub will consume. But here at Liquid, we came up with a more simple solution. We built about maybe 10 flavors because of those we need. And we have 2 minutes in average for a build. And we have all the main platforms covered because our developers using Mac, Linux, and even Linux subsystem on Windows. So we have a minimal core and we have independent the baseline, which is independent and doesn't depend on anything platform specific. If you try to get all the mentioned pieces assembled together, you'll find that you cannot do this in a single code base. You'll have to borrow something from the community. You'll have to integrate dependencies. And those dependencies will likely have issues compiling on a different platform. So we'll end up with a different CMake or whatever tool you're using for this, because it's likely C++, or maybe C, but likely C++. And you'll have to think how to arrange it, how to structure your build system so that it's actually manageable and works, and that you split things that make OS independent work and merge it with things that are doing platform dependent work. And it's quite complicated looking at the table. So we came up with a unified low-level inference. The approach is straightforward. Let's build around some known framework and enrich it. So C, C++ are the obvious choices because of the XNN Park and other things. We're using executors. I'll mention it further. Rust. What we noticed is the whole ML industry goes towards Rust, and vendors really need to consider making the bindings towards Rust, because otherwise the community tries to build them themselves. And there is an additional layer, that boundary where you need to copy the data back and forth. But don't underestimate using Rust from the beginning. It will be much easier by looking at the scope of things you need to accomplish. You have to be cross-platform, and we do our unified low-level inference cross-platform, so that anyone who develops in the same on a different machine, we expect it to run in a similar way, obviously using the same backend on different machines. Make the inference, you need to make the inference model agnostic, so that OpenAI has this chat completion specification, And it actually covers all the modalities already. So there is a way to pass an image, audio, and text and their combinations. And I don't think there is anything better than this on a simplest level. Obviously, there are MCP and other protocols that would be agent specific. But looking at this, you can achieve by mimicking what is there. And then it's very easy to use the existing tools which are tailored for this OpenAI compatibility. Not mentioning the our tool also adds some premium feature, I would call them, is lifecycle and orchestration. So some of the talks mentioned about distribution of the things and making actor-like architecture where something acts, keeps its state, shares the state. This happens on a device as well. Simplest way to look at it is when you have a device and it boots up, you need to consider whether I'm loading a model or not, whether the model is always in a hot state and is available for the inference, or it's loaded on demand. And it's a decision that every developer makes on their own, but it's not something that any current solution on the market actually suggests you how you do this. Power management. Looking at all these devices, you may not notice that if you don't tweak them, they would be slow. So very likely that if the plug is not there, or by default any Android phone would be saving power, you need to enable it programmatically. There are ways to do this. Simplest thing is increase the thread priority on the inference, so that whatever you do, whatever you're trying to compute, takes the priority and makes it the fastest as possible. Throttling. All the devices actually have throttling. And it's not something you would find easily achievable and accessible on the internet how to solve it. The problem with it is that you can even put on throttling a bigger server with 90 cores with the needed set of a load. Sandboxing, provisioning. Is the target OS you're trying to deploy ready for your application? Are there missing C Linux or other type of privileges that you're missing? How the scheduling works? Would you need to tweak a particular deployment so your application, your inference gets the best scheduling policy? All of this is covered in the platform. So how to get to the edge? You have an idea, well, perhaps you have an idea of the application, that you have a target audience. Well, you have two ways in general, to my mind. Maybe there are more. Well, there are definitely more, but main two open source things. First, we usually have a model defined in PyTorch. Well, obviously there are other frameworks, but if you define something in PyTorch, you probably can take it, or in Ajax or TensorFlow, you can define it in a PyTorch. It's your canonical way of your architecture, and you train in it. Again, if you're using a different fork, doesn't really matter. The main point I'm making here is that there is something Python, and there is something science specific that is easy to use, which is absolutely unsuitable for running on the edge. Then how to get to the edge is two ways. You either export it in some form, and PyTorch has executorch, where it traverses the graph with a sample input and tries to figure out all the operations that are needed and builds this graph for execution. So in the end, you get a flat buffers file which defines all the weights and all the chains of execution. Second way, you go with Llama CPP and GGF. You implement the model in a C++ inside of the Llama CPP. And then you assume that whatever backends and operations that exist in your model are intersecting, then that's the number of platforms you support. For quantization, you need to choose. You cannot afford a model as is. And it's a matter of trying back and forth. And it's somewhere between int 2 and maybe int 8, and in some cases FP16, where you would say, this is the quality that I would accept for my model. And it really depends on the also hardware that you target. Some of the devices may not support in 8, some of them may not support in 4, and so on. The optimizations also hardware specific. So if we look at the XNN, and there will be many kernels for instruction set from ARM to x86, and you have to choose which of those you want to apply. So enable the flags. In fact, if you're compiling for your edge on a hardware that supports more flags than, well, I'll take it this way. Sometimes you may find that when you compile a particular backend like XNN, if you don't specify flags, it will try to get these flags based on the current continuous integration machine, which might be wrong, because the set of flags that you would want to use on a target deployment might be different. And you might consider limiting them from the beginning, because the numerical correctness is not always there. We're still in the process of getting this matured, but we still observe a lot of issues as an industry and all of these frameworks that something doesn't work on a less popular platform. So we picked Executorch, and it's our bridge between the science and efficiency that they can get. Our science team, they're experimenting with operators, with layers, and they want to get a quick turnaround of how it acts actually on a target device. So if they were to use Llama CPP, they would have to first come up with a definition in Python and then implement the same thing in C++, which is obviously would take more time. But with Executorch, what they can do is make a tweak, export, and quite fast get something compiled for the target platform and measure it. So it's not just theoretical results, but efficiently knowing how it acts, how it should be. It's very fast. And the faster you can iterate on this, the more successful you are in achieving your model capabilities. Memory management. One thing that, as we all know from the past, from the web services, that efficiency comes from caching. You just don't calculate something. For those who work with Llama CPP know that there is a KV cache and there are approaches where you can sort of use slots and load, store, but it's quite complicated when it becomes non-transformer based architecture. With Executorch, there are ways how you can efficiently manage the memory by splitting the allocations of the memory per region. Example, liquid model is a combination of KV cache and SSM state. And with Executorch, what we can do, and you also can do with your model, it's not something unique to us, you can change the way this memory is grouped, and you can come up with different regions with activations, caches, and SSM caches separate. And then it means in your model during the inference, there would be an immutable state and mutable state. And mutable state is actually very small. Here is an example on this screenshot that 1B model, which is about 1 gigabyte of data, the mutable part is just 70 megabytes. And for the 3B model, which is a bit more than 2 gigabytes, is about 200 megabytes. Which means that on the edge, when we build this solution, we can achieve the edit functionality. You know, when you open the chat in Gemini and you type something, but then you return to the previous message and you say edit and tweak it and reiterate. So you're using the previous steps as a memory and then adding some, you're branching effectively, forking your way of conversation. You can do this on the edge. You can do this already today. And it's quite efficient. You are trading the disk space to the prefill. Again, many people would not, they do not see this from the beginning, that when you're working with a GPU, your the way how you prefill is so fast that it just doesn't make any sense to cache it sometimes. On the edge, it would be about speaking from minutes reduced to seconds. So obviously, if you have something that is big enough and it has to be pre-filled for 2 minutes, you'll have to do this. It might be a set of rules, might be a set of the original system prompt that contains more personal information or something like this. But if you're able to cache it, and as I mentioned, cache here is very tiny bit of the space, you then can start your new conversation always on this cache. So making you're achieving something, you're eliminating pre-calculations by invoking this, and Executorch is great at this. Okay, double slide. With Executorch as well as Llama CVP, you can get your custom operations. So it's when you're looking at a model and a scale and it looks good in Python on the GPU, but then turns out there are so many operations, so small operations that maybe they should be just swapped into a single C++ function that just encapsulates this and the whole layer is there. And again, as Llama CPP, your way is you implement everything. So you keep two sources. You have your maybe Python imaginary source where you train, and then you always adapt it. And there are some companies that are liking doing this, but with Executorch, you can always export, and you can even achieve the way where you would define a whole function, whole layer in C++, and just expose it to Python back. So whenever you are working with PyTorch, you are invoking the actual C++ implementation. So you're basically operating in Python, the C++, which is fast. And it's cool because your iterations are fast. And whoever is familiar with C++, again, it's not that complicated. It's about just kernel, few vectors that you need to do some operations on top of them. And it becomes a matter of maybe seconds, maybe a minute, less than a minute. You can do back and forth. You can make those backend aware, and you can even have a set of the same operator implemented for different backends with different delegation, which is again very cool because it's just simply on the Python level, it's the same invocation, but on the implementation level, it's per backend. So you shift it towards the library to pick the right implementation. And it makes all of this prototyping and production much easier. Here is the snippet where in Python, I'm literally copying the code from our experiment Git repo where we're loading just lib, and you see the star in the end. In fact, if we compile this for Windows or for Linux or Mac, it all works all the same. So we have people on different OS, and we are able to use Python this way to speed these things up. Another thing we do, and I think the industry will get there, is, I mentioned it as well, when you're working with a model on the edge, it's not just the model, it's a set of files associated. It matters because your model might be a set of smaller models that have built a graph on different conditions, or you have a customized tokenizer, embedder, or you have multiple models, or other things. And we have a GGUF format available from Llama CPP. And by looking at the Executorch and the PTE file, which is a flat buffers, you can extend them. And we incorporate more information in order to know what was the quantization, what was the original model, what was the path, what was the sh256 of all the files related, and so on. Why am I telling this? Well, one may ask how we get there, how we can try using something like this and deal with the complexity. And Liquid soon is going to present a platform. It will be called Liquid AI Edge Platform. Yeah, I know the name is not the greatest at this point, but we will try to get the things as easy as possible, where the Edge developer, the final application developer, would be given all these tools and even maybe precompiled binaries or sources and instructions how to build them on their own and just incorporate into their application. We see a traction of Google presenting similar to this. Telegram today announced working with Grok. They're not Edge, but perhaps they will. So we're proposing to have smaller models that are available on different quantization layers. And they're available on the edge with all these described tools in all flavors, meaning that if you pick just whatever application you want, you will get a similar experience and result using this application and this tool. It's not yet there. It would be announced separately, but from my side, it's probably it. Thank you for having me there.
So thank you, Yuri, for that was a good elaboration of the many implementation details to consider at the edge. We're running quite a bit behind here, and we don't have a lot of questions, so I think we'll pass on the questions. And thank you for your presentation, Yuri.
Thank you.
Thank you for your time. So next up, we have Roberto Morabito from Eurocom, and he's going to speak about, hi, Roberto.
Hello, hello.
He'll be speaking about the feasibility and trade-offs of language model inference at the edge. So
Yes.
Over to you, Roberto.
Thank you, Mike. And thanks a lot again to the Edge AI Foundation for the opportunity and the invitation to discuss today at the third forum on GenAI. And basically what I'm going to talk today is somehow sort of a reflection based on a series of work that together with other collaborators I've been running in the last few months, and trying to reflect a little bit on the feasibility of running mostly language models at the edge. But before digging into the main topic of the presentation, I would like to first give some context respect why we want to push, let's say, generative AI at the edge. Here I'm talking in general about generative AI, but essentially the same consideration can apply to language models. And my consideration is that all the pre-generative AI requirements that we had in terms of trying to reduce the network latency dependency and the cloud dependency, the privacy issue are still valid, and to some extent are kind of strengthening now for several reasons. First, there is the aspect of increasing security and privacy issue when it comes to sharing sensitive data with a cloud-based language model. If we think that nowadays we keep hearing that ChatGPT and these kind of services are, let's say, the new Google, and we perhaps tend to share sensitive data in our query. Those models are retrained using our model, and that, of course, raises a serious privacy concern. So that's obviously one key aspect. There is also the aspect that the type of services that, for example, include video assistants or immersive queries are also a big impact on the network performance. We will see shortly that the majority of these central cloud services are centralized, so the network can often become a big bottleneck in the provisioning of the services. But there is also the positive side that is one positive point that is kind of bringing the generative AI and language models at the edge, and this stems from the fact that the adoption and the development of small language model is growing very fast. So our idea is that we would like to have a generative AI at the edge, which is smaller, smarter, and closer. We have been trying to define this sort of tags for this big momentum. And obviously, the first aspect when it comes to the smaller, obviously refer to the availability of smaller language models. There are undoubtedly a big feasibility shift when it comes to small language model. Here you can see in the graph how the number of small language models, and this is definitely a sort of underestimation, has been growing steadily throughout the years. There has been actually a big explosion, especially in 2024, of different models with different type of billion parameters. And again, I'm not showing data from the 2025, but this number of models are keep increasing. So this is something that obviously is clearly affecting the increasing interest towards edge generative AI at the edge, also because of the open source framework that often these models are characterized. And then from academic perspective, this is also reflecting in very simply in the number of publications that are taking consideration a smaller language model and so the development at the edge. I mentioned before smaller and smarter. Obviously, we need to be careful that the kind of capabilities that we can get in this type of models are not always impeccable. Here, a very simple example of a comparison of a 0.5 billion parameters model towards versus 8 billion. A simple question talking about the famous football player Cristiano Ronaldo, and we can notice that in the 0.5 billion there is a clear some hallucination, there is some output mistake, a mix of languages, but we are well aware that obviously we cannot have the same quality of answer when it comes to the smaller models, but we can clearly, and this has also been mentioned already in the presentation earlier, this can be clearly affected. And just to give you a very simple example, we have been running some experiment that was the goal was essentially trying to compare respect using a very simple data set and a set of questions, how we are able to increase the accuracy of a small language model, in this particular case 1.5 billion parameters, in the moment that we perform a sort of fine-tuning or similar task. And we can observe that we are actually able to reach some level of accuracy that can be to some extent comparable to bigger model in the order of 72 billion parameters. So the main takeaway here is the accuracy gains from specialization, and this has been mentioned already earlier, and this become a key factor for the development of generative AI at the edge. Lastly, when I'm talking about closer, we are referring on the fact that we obviously would like to get rid of the centralized dependency that we have with cloud-based services. I'm showing here an example of a massive outage in the OpenAI services that has happened in December. 4 hours approximately, many of the services were offline. These are obviously caused a lot of problem for, especially for companies that are nowadays are using OpenAI API already in their services. And this somehow also connect to the aspect of trying to democratize the use of generative AI. We realized that studying a little bit the infrastructure of these cloud-based services that the majority of these are not necessarily relying on the content delivery network, but when it comes, for example, to ChatGPT, mostly all the servers are currently located in, for example, in the US, but we have similar setup also for other other services similar to ChatGPT. And obviously, this can impact the quality of experience that the end user like us can have when dealing with these services. We have been running some very simple experiment trying to query ChatGPT, Claude, Perplexity from different areas of the globe, and obviously there is this strong dependency from the network latency. We shouldn't forget that we are immersed in this sort of distributed architecture, and as we heard earlier, we are going towards this Internet of agent. So the network latency is extremely important, and obviously we want to avoid that the quality of experience of our language model services is affected by it. So these are somehow like the three main reasons why we see that the generative AI at the edge is a big possibility, and we should really push all the effort that we have also seen in these 2 days from the companies and researchers for making it reality. Obviously, there are a lot of trade-offs, and in the remainder of the presentation, I'll try also to discuss about these different trade-offs, especially when it comes to the feasibility. We have been performing a very extensive study that I hope you'll be interested to read. Essentially, we wanted to understand what are the different trade-offs when it comes to computation and performance limit of executing language model on edge devices, on a different set of edge devices, and considering a wide variety of model, but also how the system configuration of the models, for example, the quantization, the number of trading, affect the efficiency. And trying to gather this information also for come up with some concrete metric on what are the trade-offs in terms of latency, energy, usability, and actual cost. Let's not forget that we pay the services that we are requiring to the cloud, but in practice, even if we would run a language model in our smartphone, eventually there is a cost also for running those models there locally because of the energy, the battery cycle, and so on and so forth. So in these studies, it's quite extensive, so I really won't go through the details. We've been considering 2 single-board computers like Raspberry Pi 5 and Jetson Orin Nano. Also because we wanted to essentially compare what happened when we have devices which are only relying on CPU for executing language model inference, but also compare their performance with devices that have some sort of AI acceleration like GPU. And in this study, we have been taking consideration approximately 10 language models with parameters ranging between 0.5 and 9.2 billion. And another aspect that we wanted to understand was how modifying very simply the quantization of the model can affect, and to what extent can affect the performance. Once again, the study is very extensive, so I will just provide a very few results in this presentation. But just to show you some graph here, we are comparing the inference time for Raspberry Pi Orin, the Jetson Orin, when executing inference on the CPU and when executing it on the GPU, and for the 2 different type of quantization. There are obviously some results that perhaps were expected already before the study, like the GPU inference constantly achieve better throughput, better and more and lower inference time compared to the CPU power inference. But we wanted to understand to what extent, what's the factor, the increasing or decreasing factor respect to these 2 quantities. And also the importance of the quantization. There is always trade-off when we choose different type of quantization in the quality of the response, for example, in this specific case, but there is also an impact from a performance perspective. Here we can observe that the latency, the inference time is essentially odd between the 2 different type of quantization. So that's a very big improvement in terms of efficiency. There is clearly trade-off in terms of quality. And we also noticed that the token throughput and by reflection also the inference time, those are somehow linked. There is this sort of hyperbolic relationship that increases with the number of threads. So this was an aspect, the inference latency that we wanted to take in consideration, but also the energy efficiency was something that we really wanted to consider in our study. And in this particular case, we essentially computed the energy in joule per token, still comparing the same type of devices, the same type of quantization. And we noticed that, for example, when looking at the reduction in terms of energy consumption, both in the phase of pre-fill and generation, there is some substantial savings that we can observe just varying the type of quantization, savings that can range even between 10 and 70% in the case of the generation for the CPU-powered inference, 20 to 40% in the case of GPU. And here one main takeaway is that the faster isn't always the more expensive, in the sense that higher power modes often save energy per token by shortening the inference time. Another trade-off that we wanted to evaluate in this study was because a CPU, for example, can be set to different type of power mode, like top performance or on demand or power saving. We wanted to quantify what's the difference, what's the impact of tuning the CPU governor in particular for in terms of measuring the impact in terms of energy, inference time, and token generation. So taking consideration all these empirical results, you will find more insights in the paper. We definitely kind of can summarize that we have several trade-offs when we want to start thinking about deploying systems that are distributed at the edge in this type of very constrained devices. We have from one side the quality. We have seen that there is the type of hallucination are more frequent compared to cloud-based services, but also there is a problem of accessibility, because obviously the network is an issue when it comes to cloud, but at the same time the type of task that we can perform on edge devices is obviously limited in terms of concurrency, for example, if we compare to cloud services. And what we come up, and this is obviously just a preliminary study, is that in order to take in consideration all these different trade-offs, we really wanted to come up with some sort of unified metric. I really believe that in the future, when we will deploy hybrid edge cloud-based model, we will really need to rely on this sort of combined metrics. In this case, we define a utility function that take in consideration the quality of the response, but also the responsiveness of it, like time to first token or the token generation speed. And again, taking into account the energy usage or the API usage cost, we came up with this idea of defining a performance cost ratio. And just relying on the data that we were gathering in our empirical studies, we actually come up with some interesting results, because essentially we figured out that despite a lower quality score, because obviously we kind of give up something in terms of quality when we are running inference at the edge, the edge platform actually achieve a drastically higher this performance to cost ratio, because of the kind of lower operating cost that we have compare to cloud. So this is something that it really kind of give a hope that obviously we can start thinking about deploying this type of edge first system. And obviously the quality is something that we should always keep in mind. In the previous forum, I had a chance to present a work in which we have been using code GPT for code generation purposes, and the main goal was for us to automating embedded machine learning lifecycle task. At the time I was presenting that, for example, the generating sketch for Arduino, the executable code for running a TinyML task had 30% of accuracy when using GPT. We did essentially additional work, and we started using also small language model in the type of pipeline system. And we noticed that the accuracy was actually very, very low. So the quality, it's something that we shouldn't forget. And the main takeaway is that if we have very high precision task, the small language modeling falls short. So we really believe that there's no, at the moment, the possibility to have a fully reliance on cloud. And to this extent, essentially, taking consideration the resource scarcity, the complexity of the task, the device heterogeneity, we started another study for trying to understand what are the different strategies when we have this sort of distributed environment, distributed AI, GenAI environment. What are the strategies that allow us to minimize the cloud dependency and in turn the cost, still trying to maintain a certain efficiency, minimizing the cost, but preserving the user experience. And what we did was essentially trying to study with a small cluster of 8 edge devices and a different type of parameters like different distribution for the query, taking consideration high capacity device, a medium capacity, and low capacity device, in this case, like with NVIDIA Jetson AGX Xavier, Jetson Orinano, and Raspberry Pi, trying to understand what are the device selection strategies that we need to approach and can give us better results in terms of minimizing the cloud dependency, especially when it comes to the cost. So we decided to use to evaluate different selection strategies like random. We assign the task, the query randomly to this cluster of devices, or we prioritize high capacity devices, or load aware. So we adapt in real time to the device availability. And also in this case, we got very interesting insight because obviously it's clear that the random assignment is not going to be the most effective. But from this study, what we learn is that also based on the type of query distribution that we have in our system, whether these are steady or bursty, we need to select a different allocation strategy in our cluster of edge devices. Here, just some empirical number, but what we want to evaluate was essentially how we are able to minimize the cloud dependency, the cloud cost, and that's why you can notice on the left, for example, how many requested were rejected in our edge cluster, how much was the cost of the redirection to the cloud because the edge resources were saturating, and also on the right, what's the best strategy for using in a fair and proper way without underusing or overusing a specific node, what's the best strategy, allocation strategy to approach. So this was an empirical study for trying to, and there is obviously a lot of work that can be done, and because of the heterogeneity of the devices, there will be other devices, other type of tasks that in the future will be merged in this type of edge deployments. But essentially our next step and what we believe will come next, and this has already been envisioned today during several presentations, is that collaboration and this sort of edge to cloud, but also agent to agent collaboration will be something that in the future deserve further study. That's essentially the type of scenario that we envision in the future: collaboration edge to cloud, because of the quality of experience and quality of system that at the moment cannot be ensured always at the edge. We will need to rely necessarily on the cloud for certain specific tasks. For example, I showed the case of the automation of the code generation. If we have like a very strict requirement in terms of quality of service, we need to split our reasoning between edge and cloud. And in this work, what we have been doing is also trying to envision collaboration types between agents that are not only confined to simply offloading, as it happened between edge and cloud, but also in terms of data sharing, of course, taking into consideration all the security aspect, knowledge sharing, and cooperation sharing. This is just an example of this one cooperation approach, this computation cooperation, distributing the task among different type of agent, coordinated reasoning between agent. On the bottom, you can see a very simple example where we have a complex query that can be decomposed in different subtasks based on sort of domain matching agent. I think this resonates also well with what we have seen earlier with Nanda type of architecture. And I really believe that this is the direction where we are heading because of the intrinsic limitation that we currently have in edge deployment, both in terms of performance, but also in terms of quality of the responses. And looking a little bit ahead and somehow to making a perfect use of the different empirical evaluation that we have been doing in this different type of work, we are actually now working on developing emulator simulator, essentially, that kind of gets as input all these empirical evaluation that we have been doing in order to possibly customizing the type of devices that we have in our edge cluster, the network delay, the agent configuration. For example, we are having an Edge AI Foundation expert or a generative expert, but also the type of query input, if it's question answer, a reasoning query, a code generation. We have empirical results that can help us to somehow build and approximate the type of system and looking at the different strategies that can be applied in terms of distribution, still for reducing the cost and the dependency towards the cloud. So just to some final closing reflection, I wanted to essentially highlight three main words when it comes to generative AI and language model at the edge. And that's basically come from our experience, from what we learned. These three words are feasibility, trade-off, and collaboration. There are definitely, there is the possibility of already running successfully and with very good performance or satisfactory performance, let's say, generative AI and language model inference at the edge. There are obviously trade-off in terms of the quality of the answer that we can get from this smaller language model, but also because of the hardware limitation that we have in these devices. We still believe that at this stage, sort of hybrid edge cloud is this type of setup that we will see in the next few years, but we definitely are heading towards this agent-to-agent cooperation in different facets, whether it's computational knowledge, sharing data for improving and getting a better answer. This is definitely a very exciting area that we are pretty sure is going to happen very, very soon. And I'm almost done. I would like just to thank all co-authors and collaborators of this different work. You can find here a reference to the paper that made up this presentation, and I'm done for today. Thanks a lot again.
Well, thank you, Roberto. That was a very interesting presentation. I applaud your efforts to define some metrics for measuring the differences between the edge and the cloud, and all your work on the hybrid aspects of that. I think that's an interesting path to pursue. We don't have any questions here in the chat. I had one. Just the last thing you covered, that agent edge sim. Is that is that a tool that's to be used to design new edge systems or evaluate the performance of edge systems, or both?
Yeah, basically the idea of the simulator came from the fact that well, the background here is to trying to build distributed edge AI networks, right? So we did, and we run a lot of empirical evaluation using different type of devices, different type of generative AI workloads. So we have a lot of data that can help us to customize and emulate real devices. So this type of we envision that this type of emulator can help us to sort of design the type of network that we will have in the future, right? We certainly have, and we have seen in Nanda, some sort of semantic requirement when it comes to the design of the network, the different agent, who is doing what. But then we also have the physical constraint, the hardware, the software, the capabilities. Not always perhaps the nodes, especially in the case of edge, are available and able to satisfy multiple requests in parallel. So we will need to deal with this type of trade-off in the future, or very simply, when we think about smartphone, the battery cycle of our devices. So the idea is trying to develop this type of system that can help us to build hyperscale distributed GenAI edge systems.
Great. I'm gonna have to go look at your papers. I find that very interesting. So thanks again, Roberto.
Thanks a lot. Thanks a lot again for the opportunity.
So next we'll move on. Our last but not least presentation for the day, Andrea Basso from MITO will be talking about
and actually, this is a project that has been done as part of the PNNR financing. It's a POC that that really focused on agentic AI. Now I have these slides on my computer. Should upload them, or
you can just share them? That's probably the best way to do it. Yeah.
Okay, and I do that on present share screen. Okay, perfect. Window. Here we go. Perfect. Okay, I hope you can see it. Yes, perfect. Okay, so after all the theory about agentic AI given by the excellent speakers before me, I'm gonna just focus on a real application. So what we wanted to do in this project is actually get our hands dirty and see if we could make it work, and build an agentic AI system for a real world problem. So part of this project, it's a collaboration with Turin Airport and ST Microelectronics, as well as Eurix. And at a certain point, the airport said, we have this problem is checking the boarding process. When people get to the gate, it's always a mess. They don't stay in line. People is everywhere, and this is an issue of delays that the flight has. I didn't know that before, talking to them, but we thought that would be a very good case for testing multiple agents that interact together, that have a look on what the situation is. And a boarding may actually last even half an hour or 1 hour, and monitoring it, and then taking decision on when actually to alert the airport. Imagine that also the boarding process, it's quite complicated because it's managed by different entities. There is the airport handler, there is the airline that is responsible for managing the tickets, and so on. And there is not always coordination among them. So that was a perfect case for generating something that would improve and streamline this process. Now I don't want to go through all the details about the boarding, but I guess you are familiar. Now this happens in stages. There are priority boarding, then the families with children that typically run around, and you need to collect them and bring them on the plane. Then people with limited mobility, and then finally the economy class. No. And of course there are rules, but in general the most precious thing is having patience, so that you can get on the plane. In general, there are rules, so you're supposed to stay inside the pathways. Typically, these carry up to 150 people. And everything should happen in stages correctly. And you always have people that maybe stay seated till the last moment, and then they join. People that instead is in the line like 2 hours before the actual boarding, and occupy the places. So a lot of issues that may cause problems. And apparently this is an issue in terms of flight delay. And the other thing is that the boarding for low cost is quite different than the boarding for full service airlines, that in general is much more comfortable, more organized. And instead the low cost airlines tend to really focus on they are low cost for something, cost saving measures. So you typically have to walk a lot. It happens in stages. And in general, you wait you wait a lot. That actually is not a good user experience. That is somehow in the counterpart is the fact that you pay the ticket much less. So we also had to differentiate between this different situation. And this is what it typically looks like. This is actually the Torino airport where we are implementing this solution. So you see, people be inside the pathway, the blue pathway, but they are all outside and mixed with the other flight at the gate 19 here. So we said this is a perfect way for having multiple agents that can operate completely at the edge. So being able to do all the computation and all the communication at the edge without any cloud interaction. That was also, a very good reason for using robots. In fact, we are using moving robots, and why we're using moving robots is because we can position them in different areas and with different perspective, because of course you need to understand if actually the situation is critical or it is just temporary, and so it doesn't require any kind of actions. And also, given the expertise of the group, it was a perfect way of merging all the know-how that we have, in computer vision with the know-how that we are developing with Agentic AI and small language model. And in addition to that, we put quite a bit of pressure on us, because we're gonna do a real demo on July 15 on the at Torino Airport. So if you are around in the morning, July 15, in gate 14 to 17, you're gonna see robots going around using the architecture that I will describe here. So just to give you a sense on how this is structured, we have multiple agent, and our agent here is composed by three key modules. One is the AI vision model. This model runs advanced YOLO architecture and does all the detection and monitoring of the crowd in real time with a proprietary algorithm that we developed. Then, here we have a group of robots, and despite A2A, MCP, and all the kind of protocols that are available today for interaction among agents, here we need to have systems that are able to respond in real time and take decision. Imagine that a robot breaks, or battery is running out, or a kid start touching the camera, so things like that. So to manage this kind of interaction, just the agent side wasn't enough, because imagine these at the edge. We heard the kind of latency, the kind of processing requirement that are made, but this is not sufficient, in fact, in general, for managing real-time situations. So we added another component, I would say, to the agent that we call aggregate programming module, that manages all the real-time situation, and it does it using this aggregate programming model that is a distributed model, where every node is a cell and is cooperative together, but is able to respond much faster than an agent in this case. And then at last, there is a small language model inside the agent that takes the data that come from the AI vision module and does a deeper interpretation. So the AI vision model is able to immediately detect it's operating, at 30 frames per second. So it's able to detect a normal situation quite quickly. But of course, it extracts some parameters from the crowd analysis that we do over there, but is not able really to do an analysis as complete as a small language model can do. So the image, together with the ancillary information that we extract from the AI vision model, is passed to the small language model that then analyzes it and does a first estimate of the situation. It may be critical or non-critical. If it's non-critical, then nothing is passed at the subsequent layer, or if it's that critical, then it is passed at the consensus layer. And this happens from all these robots distributed in the boarding area. So if the agent reach consensus on the fact that the situation is critical, then at that point the system automatically generates an alarm, and then there is a reaction from the personnel. And as I said, there is a coordination among the agents through the agent layer, but also through the aggregate programming layer to manage critical situation. So just to give you a sense on the hardware that we are using here, thanks to the collaboration with ST Microelectronics, we ported the vision component to an STM-N6. I will show you in a second. And the detection system really use a modified YOLO. We tried actually several versions. Not all of them can run on the STM32N6, but all of them they run on the Jetson Orin. Plus, again, the part of crowd management and detection that I will explain in a second. Then, in terms of the agentic AI, on one side we use a laptop with NVIDIA RTX 4070 for running the small language model and consensus layer. But also we are strongly experimenting with a much smaller and cheaper solution like the STM32MP2 257 to be exact series that has a dual core ARM-like core that is really very power efficient, and just to give a sense, the processor doesn't heat at all, so it's always really cold, and I'm amazed on how that can be while we run, a small language model. Just to give you an idea of the robot that we're using, we have some medium-sized robot that is the ClearPath Jackal, as well as a very small one that carries everything on board. You see the Jetson Nano on the top, a big, huge battery pack for powering the Jetson and all the other components. There is a two-layer behind the white layer. There are another mini PC plus LiDAR and other components, and then of course cameras, and all the processing actually happens on board. The Jackal actually has a PC with a 4047 RTX 47 on board. So just to give you a sense on how we structure the computer vision model that is part of the agent. The part of detection, as I said, it's an optimized one class person only model that again operates practically in real time. So we are talking about 30 frames per second. And the approach that we followed for that, if you look at the literature related to crowd counting and crowd management before YOLO, so before like 5 years ago, something like that, it's amazing. There are hundreds of algorithms that have been developed. Actually, at the bottom of the slide, you can see a nice survey of deep learning methods for crowd counting analysis. But we decided that definitely we can do differently, and with using really current technologies, given that AI had such improvement and growth in the last few years. So mainly we do just the counting of the people using YOLO, and then we developed an algorithm that takes into account the formation of the crowd. The fact that the crowd is not really continuous, but may be constituted by small groups, very tight together. You can imagine a family, it's all close together. Then there is a gap and maybe another family or another single person and so on, but it's still a crowd. It's still the entity that we need to track. And so considering that the fact that if you are standing for half an hour, you tend to move, you tend to maybe hide your face and things like that. So that adds a dynamic of the crowd that we had to consider, and the algorithm actually does all this. And of course, the fact that this crowd is formed and it stays, so it goes beyond what should be the right way of boarding. It's another important parameter. So we actually filter out. There is a kind of low pass filter that filters out all the instantaneous peak of flash crowds or similar situation, just to avoid to generate false alarm to that. And here it's an example really taken from real video in the airport. So in this a typical typical situation that need to be managed because all the people is actually not in the proper position. As I said, I really appreciated the talk from Yuri from Liquid AI, because I empathize a lot with the pain that a programmer has in bringing AI to the edge. We experience this continuously in bringing AI on the Jetson Nano and on microcontrollers, because you need to take into account a variety of parameters that do not necessarily exist when you are in the cloud. Imagine also just the power consumption. We actually had thermal plans for, and given energy amount allocated for all the devices. Otherwise, the robot would run out of battery very, very quickly, in particular the small one, and they need to be operative for hours to be really effective as a solution. So anyway, this is just a snapshot of the development board from ST running our crowd detection algorithm. And then, of course, there is the integration with the small language model, and mainly, here we need to shrink, in fact, the domain in which we were operating, just to make it efficient. And in particular, we wanted to have these are vision LLM. We need really to focus on the capability of the small language model to do the scene interpretation. And also for us, it wasn't really relevant to get long description of what it was happening, because in the alarm we would attach the image also for the airport personnel, but mainly we wanted to have a decision taken by the agent, the agentic system, that in fact that was a critical situation. So here I want to give you an idea on what we used for this. We use RAG in this scenario. And so we use as vector database. There was during the talk, I really enjoyed the talk from Aruna from Dell, in which all the different blocks that you knew were described, and in particular one of them was really the vector database, that is used for retrieving semantic document embeddings. So that we use that model connected through local ports. We used Ollama as environment that would run the model. A web interface, of course, and all the communication between the different models, as well as with the robots, because you have to imagine that the robot run their own operating system that's called the ROS, and we ran a version of ROS that is Habo, and that also is a pub-sub model. And in fact, we need to make coherent communication among different paradigms, among the agents, among the low-level robots, and also the aggregate programming. So we had like 3 layers of communication, considering that they need to operate in almost real time for definitely the ROS part and the aggregate programming part. Instead, the time constant for the agent, the fact of taking a decision, is not necessarily in real time, because you at least need to wait 10, 15 seconds or more to understand if the situation is actually becoming critical or not. And we use the Agno as a multi-agent framework for architecting the system. Just to give you a sense on what the optimization we made for the model. Of course, we heard during I think these 2 days how quantization it's important. So it is a must. In fact, how you can manage the attention components for the SLM, the reduction of vocabulary, because of course you don't need an SLM that is talking Swahili here, but really focus on the detection, interpretation of the image. And also we did quite a bit of optimization on the code. In particular, what I did recently, and Danilo was so kind actually to publish it on LinkedIn. We did a variety of optimization, in C++, of course, being able to run Llama CPP, Gemma 2 at 2 billions, Qwen at 500,000 parameters, and more recently BitNet that is quantized at 1 bit. With interesting result. We are not there yet for this part, so we are still running the models on the laptop, but I'm confident that we in time will reach also the capability of running this model in very simple hardware. This is what is the workflow of the system. So there is detection and monitoring that is happening in real time. All the candidates are then analyzed by the agent using the SLMs, and then there is a consensus layer that is the one that actually then drives the alert to the airport personnel. And this is the last slide. We cross the finger, wish us luck. We're gonna have a live demo, featuring this system the July 15, and there will be an event, I think July 18 at the Turin airport. And hopefully, everything will work well. I mean, we did quite a bit of tests, so somehow we are confident. But it will be a good test bed, to see how far we are with our system. I want to thank the organizer for inviting me. I found the content really great and interesting, and I really am a strong believer of Edge AI and Agentic AI. And also I think that small language models and LLMs are just a first step. You have to consider that are statistical models that operate on large amount of data that is really unstructured. So they do what they do because they have this amount of data in which they can navigate. But there is a lot of research going on in trying to optimize and prune this information in a very smart way. And looking at the structures that the data has, really to simplify the process. Today, the approach is still really brute force. I would say it works, but it's brute force. I believe definitely we can do better than that. Okay, and with this, I think I'm done.
Well, thanks again, Andrea. It was good to see a real life use case for
Great.
For Edge AI. I don't see any questions in the chat, but I have a couple, and I'm sure Hajar and Danilo may as well. So how many of these robots are in a given area? I mean, is there one that moves around, or?
No, we're going to have between 2 and 3.
And that's per gate area?
Yes, per gate. Yeah. And actually, just a small swarm of 3 robots is fine because it can do one boarding and then move to the next gate and do the other boarding.
Got it. And then what's the, is there an estimated quantitative benefit? I mean, so you're trying to, I guess, reduce boarding times is the ultimate goal. So do you have an estimate of like, will you improve it by 10%, 20%, or you're going to find that out when you do the test?
Yes, I mean, that, as I said, it's a proof of concept. So,
yeah.
But the estimated, it's around 20%, 25%, because one of the issues that apparently happens, and I'm just reporting it, so is that even that there are several players, during a boarding process, there is the handler, the airport handler, there is the airline, and there are then the local support. And the interesting thing is they do not necessarily talk together, effectively. And sometimes there is no alarm that is triggered when it should. And so this makes, it is a problem because there are different, really different coverage in terms of responsibilities. So we hope to make a step forward on that.
Great. Well, thanks again, Andrea. Very interesting.
Thank you all.
Thank you, Andrea.
I enjoyed. Thank you.
Hello, Hajar. You have any comments, questions?
I think it's been a great day and very packed with lots of contributions. So first of all, congratulations to Hajar and Mike for moderating lots of outstanding talk today in about 4 hours. 4 hours.
Yeah,
Went a little overtime, but that's okay. It was worth it. It was worth it.
I think we explored like the full spectrum from on-device intelligence, decentralized AI agents, model compression, cross-industry applications. I mean, it was really awesome.
Yeah, it was interesting for me to see the evolution of this forum. This is the third one. We think about the first one we did back in spring of last year, very kind of proof of concept, can you even run language models on these platforms? And now, like Hajar mentioned, we're really talking more about solutions and agentic AI and deployments and things like that. So it definitely feels like this is starting to kind of get some legs and some maturity to it, and people are thinking about it more holistically, especially as it extends cloud AI into the real world, right? And complementing what's happening in the cloud. So I thought that was really cool to see some of the evolution of those talks.
In fact, some of these talks proposed solutions that harmonize fixed AI with generative AI, and within a system approach. So these are not one versus the other, but all together. I think just to mention the last example, Andrea Basso was showing, actually they coexist within an overall approach, and in particular on premises. On premises, as Evgeny elaborated a bit, I think is super important because the airport is a fantastic example of on-premises AI deployment site. So things start to be together, and we can view all of that within a solution approach.
Also, Pete and Danilo, I think the future of Gen AI isn't something that we can only discuss. It's something we should build. And we, at a certain point, we have to take everything we've learned in this forum, everything we've questioned, what we imagined, and maybe carry it forward into our research, into the products, into maybe the collaborations. And this is what makes this community special.
Yes, no, I agree. I am a little in the airline boarding thing. I guess I fly so much. I'm concerned about I will have AI agents kind of making decisions about who gets the upgrade, and I can't kind of talk to the person behind the counter anymore. I don't know. We'll see what happens.
Yeah, that's likely to happen, I guess. Yeah.
Yeah, but But no, it's inevitable, and I think and then we're all about connecting AI to the real world, right? So this is all the discussions about how this stuff lands in the real world, and yeah, no, I'm looking forward. We got to set a date now for the next one in the fall, so we can see what else is going on, because I'm sure by then there'll be a whole new set of conversations going on too. So it's pretty exciting.
Yeah.
I would say as a PSA for those that have joined us for the first time today, come to edgeaifoundation.org, visit our website, come to our event in Milan, July 2nd through the 4th, join our Discord server, dsc.gg/edgeai. I'll put that in the chat. Subscribe to our YouTube channel, buy a t-shirt, I don't care, whatever. So just kind of get involved, because this is definitely a collaborative operation here. It's a team sport. As you can tell, all the conversations today from around the world, people working together, which we have to collaborate to make this stuff work. So I encourage folks to lean in and join the community in some form. So
yeah, and of course, a big thank you to the speakers, all of them. The presentations are brilliant. The organizing team, the TPC, Rosina in the background, the moderators, Mike, Pete, my dear Danilo. Thank you very much for your collaboration and dedication to this forum. And it was a real pleasure working with you.
As well, Ajar, always a pleasure to cooperate with you.
Cool. Well, I guess that kind of wraps it up. So should we just kind of close it on down here? And I'm going to go have lunch. I think you guys are going to have dinner. I don't know.
And see you in Milan. Come in Milan.
That is it.
See you at the next one.
That's right.
Okay.
All right. Thanks, everybody.
All right. Bye-bye.
Bye.
Yeah.